What if I told you there are places in the universe where gravity is so strong, it literally rips holes in the fabric of space and time? Places where not even light can escape. Today, we're starting a journey to understand these cosmic monsters called black holes. And we're beginning with the most fundamental question. How did we go from thinking of gravity as a simple force to understanding it as the curvature of space itself? Gravity seems simple, right? What goes up must come down. But when we try to understand black holes, Newton's idea of gravity completely falls apart. Imagine trying to explain a smartphone to someone from the 1800s. They just wouldn't have the concepts to grasp it. That's where we are with gravity and black holes. Newton's laws work fine for apples falling from trees, but they completely fail when we try to understand what happens at the edge of a black hole. So what's the problem? For over 200 years, everyone believed Newton had gravity figured out. His laws described how objects attract each other with a force that depends on their mass and distance. This worked perfectly for almost everything we could see. Planets orbiting the sun, moons orbiting planets, even comets zipping through our solar system. But in the early 1900s, scientists started noticing tiny problems with Newton's theory. Mercury's orbit around the sun was slightly off from what Newton predicted. And when astronomers discovered light could be bent by gravity, Newton's equations just couldn't explain it. The real challenge came when we started asking, what happens if you squeeze so much mass into such a small space that gravity becomes infinitely strong? Newton's laws predict that the gravitational force would become infinite. But what does that even mean? How can a force be infinite? And what happens to space and time when gravity gets that extreme? These questions pushed scientists to the breaking point of Newtonian physics and forced them to think about gravity in a completely new way. This is where Albert Einstein comes in. In 1915, Einstein proposed something mind-blowing. Gravity isn't a force at all. Instead, gravity is what happens when mass and energy curve the fabric of space and time. Imagine space and time as a flat rubber sheet. When you place a heavy object like a star on it, the sheet curves. Planets orbit the star not because of a mysterious force, but because they're following the curves in this warped space-time. This was a complete revolution in how we think about gravity. But how did Einstein come up with this idea? It started with a simple thought experiment. What would happen if you were in an elevator in deep space, far from any gravity? You'd feel weightless. Now what if that elevator started accelerating upward? You'd feel a force pushing you down, just like gravity. Einstein realized that acceleration and gravity feel exactly the same. This became his famous equivalence principle. This insight led him to realize that gravity isn't a force pulling objects together, but rather the curvature of space-time itself. Einstein's theory, called general relativity, made some wild predictions. One was that light should bend when it passes near a massive object. In 1919, astronomers tested this during a solar eclipse. They measured the positions of stars near the sun and found that their light was indeed bent by the sun's gravity, exactly as Einstein predicted. This was huge news. It proved that Newton's theory wasn't the whole story, and that Einstein's curved space-time was real. But what does this have to do with black holes? Einstein's equations showed that if you squeeze enough mass into a small enough space, space-time curves so much that it creates a region where nothing can escape. Not even light. This was the theoretical prediction of black holes, though Einstein himself wasn't sure they actually existed in nature. The math suggested they were possible, but they seemed so extreme that many scientists thought they were just mathematical oddities. The key insight came from German physicist Karl Schwarzschild, who found a solution to Einstein's equations just a month after they were published. Schwarzschild's solution described what happens to space-time around a spherical mass. He discovered that at a certain distance from the center of this mass, something bizarre happens. Time stops, space becomes infinitely curved, and nothing can escape from inside this boundary. This boundary is now called the event horizon, and the point at the center is called the singularity. But what does this actually mean? Imagine you're watching a clock fall into a black hole. From your safe distance, you'd see the clock tick slower and slower as it approaches the event horizon. The light from the clock would become redder and dimmer until it seems to freeze just outside the event horizon. But for the clock itself, time would feel normal as it crosses the event horizon. It would just keep falling inward. This bizarre effect happens because gravity isn't just curving space, it's also curving time. The math behind this is incredibly complex, but the basic idea is simple. Mass tells space-time how to curve, and curved space-time tells mass how to move. In the case of a black hole, the curvature becomes so extreme that it creates a one-way membrane, the event horizon. Anything that crosses this boundary, including light, is trapped inside, doomed to fall toward the singularity at the center. But how do we know black holes actually exist? For decades, they remained theoretical predictions. Then, in the 1960s and 70s, astronomers began discovering objects that could only be black holes. They found stars orbiting invisible companions with incredible speed. They detected powerful X-rays coming from hot gas swirling around invisible objects. And most recently, in 2019, the Event Horizon Telescope actually captured an image of the shadow of a black hole in the center of a galaxy called M87. This image showed a bright ring of light bent by the black hole's gravity, with a dark center, the event horizon itself. The discovery of black holes confirmed one of Einstein's wildest predictions and opened up a whole new frontier in physics. But it also raised new questions. What happens at the singularity? What happens to information that falls into a black hole? And how do black holes affect the evolution of galaxies? These questions keep scientists busy today, pushing the boundaries of our understanding of space, time, and gravity. So why does this matter to you? Because black holes aren't just abstract concepts in physics textbooks. They're real objects that shape our universe. The supermassive black hole at the center of our Milky Way, called Sagittarius, a star, influences the orbits of stars near the center of our galaxy. And understanding black holes helps us understand the most extreme conditions in the universe, places where the laws of physics, as we know them, might break down. The journey from Newton's gravity to Einstein's curved space-time wasn't just a scientific advancement. It was a complete revolution in how we think about reality. Newton saw gravity as a force acting across space. Einstein showed us that gravity is the geometry of space-time itself. And black holes are the most extreme manifestation of this geometry. Places where space-time is so warped that it creates one-way paths to oblivion. As we continue our journey into the heart of black holes, we'll explore more mind-bending questions. What happens when you fall into a black hole? How do black holes grow? And what can they teach us about the nature of space and time? The answers will challenge our intuition and expand our understanding of the universe. But for now, we've laid the foundation, from Newton's pull to Einstein's curved geometry, that makes our modern understanding of black holes possible. If you want to discover what happens at the very edge of a black hole where physics breaks down, watch our next video in this journey to the center of a black hole. Black holes stand as some of the most mysterious objects in the universe, and at first glance, they seem surprisingly simple. A black hole can be described by just a few basic properties, and yet its effects are anything but ordinary. Imagine approaching one of these cosmic enigmas. What would you find as you draw closer? Black holes, in theory, are elegantly simple. They can be completely described by only three attributes. These three properties, mass, spin, and electric charge, are like a black hole's identity card, the only traces left of all the stars and matter that fell into it. Mass is the first and most obvious attribute. It is a measure of how much matter, or energy, the black hole contains, and it dictates the strength of the black hole's gravitational pull. The greater the mass, the more extreme the curvature of space around the black hole, and the larger the sphere of influence where its gravity dominates. This sphere of influence has a boundary called the event horizon, the point of no return. At the event horizon, the gravitational pull is so strong that the escape velocity equals the speed of light, meaning not even a beam of light can break free. For someone far away, the event horizon would appear as an invisible shell surrounding the black hole. There is nothing solid there. If you fell through, you wouldn't hit a wall. You would simply pass from a region where escape is possible to a region where it is not. Nevertheless, this boundary defines the surface of the black hole in a sense, containing everything that lies within. It's an eerie concept, a surface with no substance, marking where we forever lose the ability to see or retrieve anything that crosses inward. From the outside, nothing that happens past this boundary can ever affect the world beyond, which is why we call it an event horizon. Events on the other side are forever hidden. Spin is the second defining quality of a black hole. Essentially, it's how the black hole rotates. Many black holes are born from spinning stars or from cosmic collisions that impart rotation, so they carry angular momentum. A spinning black hole drags spacetime around with it, in a phenomenon known as frame dragging. As the black hole spins, it twists the space around its equator, almost like stirring a thick syrup. Except the syrup, in this case, is the fabric of spacetime. This effect is so powerful near the black hole that it creates a region outside the event horizon called the ergosphere. Within the ergosphere, space itself is being whirled around. In this region, nothing can remain completely still relative to the distant stars. Even light is dragged into co-rotation with the black hole. The outer edge of the ergosphere is where this dragging effect becomes overwhelming. At that boundary, the so-called static limit, space is being pulled so swiftly that resisting the drag would require moving faster than light. The ergosphere is shaped like a flattened sphere, touching the event horizon at the black hole's poles and bulging out around its middle. Within this strange zone, exotic possibilities arise. For example, extracting energy from the black hole's rotation, a feat allowed in principle by the laws of physics. Electric charge is the third and final property that can characterize a black hole. In theory, a black hole could carry a positive or negative charge, just like any normal object might be electrically charged. However, in the real universe, it's unlikely for a black hole to retain a large charge for long. It would attract opposite charges from the surrounding plasma and quickly neutralize. Still, the possibility of a charged black hole is part of the theoretical picture, rounding out the trio of properties. And crucially, aside from those three, mass, spin, and charge, no other information from whatever formed the black hole remains accessible to the outside universe. A popular way physicists phrase this is that black holes have no hair. In other words, aside from their mass, spin, and charge, black holes don't reveal any distinguishing traits. It doesn't matter what kind of star or matter went into forming the black hole. Once it's in there, all the complex details are wiped clean from our view. two very different stars could collapse into two black holes with the same mass and spin. And as far as the outside universe can tell, those black holes would be identical. This stark simplicity is part of what makes black holes so intriguing. They obliterate the rich details of the objects that created them, leaving only a pure gravitational imprint. Just outside the event horizon lurks another extraordinary feature: the photon sphere. This is a spherical region where light itself can orbit the black hole. Normally, we think of light traveling straight or along gentle curves through space. But near a black hole, the curves of space-time become so extreme that a ray of light can loop entirely around the black hole. At the photon sphere, a photon, a particle of light, can circle the black hole perpetually, trapped in a doomed orbit. It's a delicate balance. If that photon strays a little closer to the black hole, it will spiral inward past the horizon and vanish. If it moves outward slightly, it will escape to infinity. The photon sphere is like a last stand for light, a tightrope between freedom and capture. For a distant observer, the photon sphere and the region just inside it contribute to one of the most striking visual signatures of a black hole. Any light coming from behind the black hole or skimming near this region can get bent around, and some of it is sent toward an observer. This leads to a phenomenon where you might see a ring of light outlining where the photon sphere is, often called the ring of fire, around a black hole's shadow. In images or simulations of black holes, this bright ring appears because of those light orbits. Photons from all directions getting concentrated into a halo. It's a beautiful irony that something utterly dark at its core can be framed by a circle of light, a beacon outlining the darkness. At the very heart of the black hole lies the most mysterious component of all: the singularity. This is the point, or in a rotating black hole, more likely a ring-shaped region, where the mass of the black hole is concentrated. In the classical description, the singularity has no size, and density and gravity become infinite, which is another way of saying our physics theories break down there. It's a place we can't see, and perhaps cannot ever truly understand with current science. Hidden behind the event horizon, the singularity is the ultimate mystery, the central abyss that all matter and energy are drawn into once they cross the horizon. All these elements, the event horizon, the photon sphere, the ergosphere, and the central singularity, form the anatomy of a black hole. They paint a picture of a region where space and time are contorted into shapes and behaviors that defy our normal intuitions. To truly grasp how nature can allow such strange constructs, we must delve into the theory that predicted them: Einstein's general relativity. It's in Einstein's equations that black holes arise, not as monsters of myth, but as logical outcomes of gravity compressing matter without limit. While the full mathematics is complex, we can explore the core ideas of those solutions in plain language to see how they explain the existence of event horizons and spinning singularities. Einstein's general relativity reveals that gravity is not a force pulling at a distance, but a curvature of space-time itself. To navigate this curved space-time, physicists use what's called a metric, essentially a map that tells us how distances and durations are measured when space and time are warped by gravity. The Schwarzschild metric is one such map. It represents the space-time around a spherical, non-rotating mass, effectively a quiet black hole. Carl Schwarzschild discovered this solution in 1916, giving the first glimpse of a black hole within Einstein's equations. In simple terms, the Schwarzschild solution showed that if enough mass is packed into a small enough volume, space-time curves so steeply that at a certain radius, the event horizon. Not even light can escape. For a mental image of what a metric describes, imagine space as a stretchy rubber sheet. A massive object like a star creates a dent in this sheet, like a heavy ball on a trampoline. A black hole would create a deep well in the fabric, a bottomless pit where the sides grow steeper as you near the center. The metric is like a grid drawn on this distorted sheet, telling us how steep the sides are and how distances shrink or stretch near the pit. The deeper you go into the well, the more the grid lines converge and warp, illustrating why climbing out from near the bottom becomes impossible. This analogy captures the essence of what the Schwarzschild metric formalizes for a spherical mass. It quantifies the curvature of space and the slowing of time near a black hole. In the Schwarzschild description, space and time near a black hole behave in unusual ways. Distances in the radial direction, toward and away from the center, do not follow the same rules as they would in flat space. Space is stretched, and what an outside observer would measure as a certain radius might hide much more space than expected. Time, too, is affected. Closer to the black hole, clocks tick more slowly, relative to clocks far away. If you were hovering just outside a Schwarzschild black hole, you would notice that your time is running slow compared to the rest of the universe. These predictions, slower time and curved paths for light, emerge naturally from the Schwarzschild metric and match what we later observed in gravitational experiments. The Schwarzschild solution also defines a specific radius associated with the black hole's mass. We call it the Schwarzschild radius, essentially the size of the event horizon. For an object as massive as our Sun, this critical radius is about 3 kilometers. That means if you could compress the Sun into a sphere only 3 kilometers across, it would become a black hole. Its gravity would curve space-time enough to trap light. Larger mass black holes have larger Schwarzschild radii. For instance, a black hole with 10 times the Sun's mass would have an event horizon roughly 30 kilometers across. This simple proportionality is one of the reasons we often imagine black holes as fairly simple objects. Double the mass, double the size of the horizon, according to Schwarzschild's formula. Real black holes in the universe often aren't perfectly still. They rotate. In 1963, New Zealand mathematician Roy Kerr found another solution to Einstein's equations that describes a spinning black hole. The Kerr metric was a milestone because it showed what a rotating black hole's space-time looks like. In Kerr's solution, the rotation of the black hole twists and drags the space-time around it. This leads to precisely the effects we discussed earlier, an ergosphere where space itself is pulled along, and a deformation of the space-time geometry compared to the non-rotating case. The Kerr solution revealed a number of fascinating features. A rotating black hole in Kerr's description has not just an event horizon, but also an ergosphere, where space-time itself is dragged around. The singularity in the Kerr geometry is not a single point, as in a static black hole, but a spinning ring. The math even suggests an inner horizon beneath the outer one, hinting at a layered interior. In these deep interior regions, the equations become very strange, even hinting at possible passageways to other universes or times, ideas that almost certainly cannot survive in reality. Still, the mere existence of such solutions fires the imagination and shows how far general relativity's predictions can stretch. In addition to Kerr's rotating solution and Schwarzschild's static one, there are solutions for charged black holes as well. These go by names like Reissner-Nordström for a charged non-rotating black hole, and Kerr-Newman for a charged rotating black hole. They introduce electric fields into the picture and come with their own subtle differences, like multiple horizons. However, as we noted, any large charge is probably neutralized in nature. So these charged black hole solutions are more of theoretical interest than something we expect to find in the sky. Still, they complete the family of black hole metrics, showing that Einstein's equations can accommodate mass, spin, and charge in various combinations. These solutions are not just mathematical curiosities. Observations confirm that they describe real black holes. Astronomers tracked stars whipping around an invisible mass at the center of our Milky Way. The way these stars move, their high speeds, and the slight wobbles in their orbits fits the profile of a black hole about 4 million times the Sun's mass, just as general relativity predicts. And when telescopes captured an image of the supermassive black hole in galaxy M87, it showed a dark shadow ringed by light, closely matching what physicists expected a spinning black hole's silhouette to look like. Observations like these give us confidence that the metric solutions are accurate blueprints of how spacetime behaves around a black hole. Through the Schwarzschild and Kerr metrics, we have a blueprint of a black hole's spacetime. They explain why there is an event horizon and how it behaves. But it's worth contemplating directly what this horizon means for anything trying to escape. Essentially, the event horizon is that critical boundary where escape velocity reaches the speed of light. To understand the finality of crossing this boundary, we should delve into the concept of escape velocity and the fate of light and signals near a black hole. In doing so, we'll see how light can be stretched and reddened, and why, once past the horizon, there truly is no return. We often explain a black hole's gravity in terms of an escape velocity, the speed needed to break free from its pull. Think of how a rocket must reach a certain speed to escape Earth's gravity. For Earth, that escape velocity is about 11 kilometers per second. For a black hole, at the boundary called the event horizon, the escape velocity reaches the speed of light. In essence, the event horizon is defined by this condition. It's the distance from the black hole at which escape becomes impossible without exceeding the cosmic speed limit. The idea of such a light-trapping object was imagined long before we had general relativity. In the late 18th century, an English scientist named John Michell reasoned that a star, extremely massive and compact, could have an escape velocity greater than light speed, rendering it invisible. He described it as a dark star, a star that we could not see because its light would be pulled back by gravity. While Michell's calculation was based on Newtonian gravity and not entirely the same as a black hole, it was a remarkably prescient insight. It hinted at the concept of an event horizon well before Einstein's theory provided the full picture. Another way to visualize the point of no return is with a river or waterfall analogy. Imagine you are floating in a river that is flowing towards a huge waterfall. Far from the edge, the current is gentle, and you can paddle or swim to safety. But as you get closer to the waterfall, the river flows faster and faster. There comes a point where the water is rushing so quickly that not even the strongest swimmer or fastest boat could fight against it. Once you pass that point, you will inevitably be swept over the edge. In this analogy, the event horizon is like that point of no return in the river. Beyond it, the flow of space-time toward the black hole is so strong that escape is impossible. As objects or light try to climb away from a massive body, they lose energy, a phenomenon known as gravitational redshift. Redshift refers to light shifting toward the red, lower energy end of the spectrum as it loses energy. Near a black hole, this effect becomes extreme. If a beam of light struggles upward from close to the event horizon, by the time it escapes to a distant observer, it will have given up most of its energy. The light's wavelength will stretch to longer and longer, redder wavelengths, and if it started as visible light, it might be shifted beyond visibility into infrared or radio waves by the time it reaches afar. The closer to the event horizon the light is emitted, the more pronounced this redshift. At the event horizon itself, the redshift becomes infinite in theory, meaning any light emitted exactly at the horizon would be stretched out infinitely and never actually reach an outside observer. In practical terms, this means that if you hover just outside a black hole and shine a flashlight away, someone far off in space would see the beam become fainter and redder, struggling to escape the abyss. If you were right at the edge, that light would almost never make it out. To the distant observer, it would be as if your flashlight just dimmed and winked out as you approach the horizon. For someone falling into a black hole, this loss of signal is dramatic. Suppose an intrepid astronaut is descending toward the event horizon and sends out regular pulses of light or radio to a distant friend. As the astronaut gets closer, each successive pulse takes longer to arrive and comes through with ever-diminishing energy. The intervals between signals stretch out, and their color shifts toward the red end of the spectrum. Just before the astronaut reaches the horizon, the signals become so delayed and stretched that they essentially fade away before ever reaching the friend. It's not that the astronaut stops transmitting, they might still be sending signals, but beyond a certain point, no information escapes to the outside world. What about trying to escape from inside? If somehow our astronaut could try to fire thrusters or shine a light once they've passed the event horizon, would it do any good? Unfortunately, no. Inside the event horizon, the flow of space-time carries everything inward. Just as nothing can prevent you from moving forward in time, nothing can prevent you from moving closer to the singularity once you've crossed that threshold. Any rocket burn, any light beam you aim outward, will still end up heading further in. The concept of escape simply no longer exists inside that boundary. All paths lead deeper in, the way future moments lead inevitably to later times. It's important to note that the event horizon is not a tangible surface. If our astronaut crosses it, they don't smack into a wall. Space doesn't suddenly change its texture. To them, passing the event horizon might feel like nothing at all unusual in that exact moment. There are no signs saying you are now entering a black hole. The effects, like light being unable to escape or time behaving oddly, are something an outside observer notices about that location in space-time. For the person falling in, the crossing is geometrically significant, but locally unremarkable. This makes the idea of the event horizon even more haunting. One can drift past the point of no return in total silence and without immediate drama, only to find that the way back is truly gone. Thus, the edge of a black hole is a one-way membrane in the fabric of the universe. Cross it, and you are forever cut off from what lies outside. No message, no light, no influence you attempt to send can bridge that gap once it is crossed. The event horizon marks where gravity's grip becomes absolute. It defines the black hole's surface, in a sense, the ultimate border between the known universe and the unknowable interior. Beyond trapping light, a black hole's gravity also wreaks havoc with space and time in other ways. Clocks near a black hole tick at different rates, and the very appearance of the surrounding universe warps for an observer plunging inward. The bending of light, which makes the black hole act like a lens, and the stretching of objects by tidal forces are other strange phenomena in the vicinity of these cosmic abysses. Now, we will explore these peculiar effects on time and space more deeply. We will see how black holes can slow time to a crawl, deflect light into surreal patterns, and pull matter apart atom by atom. A black hole's influence on time is one of its strangest effects. We've mentioned that time appears to slow near the event horizon from the perspective of a distant observer. This gravitational time dilation means that a clock placed near a black hole will tick more slowly compared to one far away. If an astronaut could hover safely outside a black hole, say at a safe distance, but still in strong gravity, and then return to Earth, they would find that less time passed for them than for everyone who stayed behind. In essence, the black hole can act as a sort of time machine to the future. By hanging out in its intense gravity, one could leap forward in time relative to the rest of the universe. The closer you get to the event horizon, the more extreme the time difference becomes. In fact, in science fiction or thought experiments, one could imagine orbiting just outside a black hole and then coming back to see the future. A famous example of this idea appeared in the film Interstellar. Astronauts visiting a planet near a massive black hole experience hours which correspond to years back on their ship and on Earth. This dramatization was based on real physics. Near a black hole, time for those close by passes much slower. While the movie took some creative liberties, the core concept is valid. A strong gravitational field can make 1 hour for you equal 7 years for someone farther away if the gravity is extreme enough. From the perspective of a distant observer, time at the edge of a black hole almost comes to a halt. If you watch a spacecraft fall toward the event horizon, you would never quite see it cross the boundary. Instead, its movements would slow down more and more as it approaches the horizon, and its onboard clock would appear frozen at the moment just before crossing. The light from the spacecraft would also grow redder and dimmer, making it effectively vanish from view. To an outside observer, it's as if the falling object becomes suspended in time at the brink of the black hole, faded and motionless. Of course, from the object's own perspective, it continues inward in a normal passage of time. But this disparity in views is a hallmark of general relativity's warping of time. What if you were the one near the black hole looking outward? Your own time would feel normal to you. Your heart would beat at a regular rhythm. Your clocks would tick along as usual. But if you could observe the outside universe from deep in the gravity well, you'd see things moving faster. The distant universe would appear to speed up. If you hovered near an event horizon and looked back toward Earth, you might see the future of Earth unfolding at an accelerated pace, like a time lapse. This is the flip side of time dilation. Others see your time as slow, while you see their time as fast. In theory, one could watch the stars age rapidly, or galaxies evolve if you were able to survive long enough near that extreme gravity and then escape it. Gravity doesn't only slow time, it also bends the path of light. A black hole's intense curvature acts like a lens, deflecting light from background stars and galaxies. This gravitational lensing can produce strange visual effects. If a black hole passes between us and a distant star, it can distort the star's image, smearing it into an arc, or even creating multiple images of the same star. In deep space, entire galaxies can act as gravitational lenses too, magnifying and warping the light of more distant galaxies behind them. Black holes are the ultimate lenses. Their gravity is so strong that it bends light almost as easily as a glass lens bends a beam in an optical experiment. Near a black hole, the view of the universe around you would become profoundly distorted. Light from objects behind the black hole can be curved around and reach your eyes, meaning you could see part of the backside of the black hole's environment. You might witness a ring of light, an Einstein ring, formed by an entire background galaxy's light being warped into a circle by the gravity. If you looked toward the black hole itself, you'd see a dark central spot, the shadow, surrounded by a surreal, smeared image of the sky around it. Stars might appear as streaks or multiple points of light. In a way, the black hole acts like a funhouse mirror for the heavens, warping and duplicating images of anything behind it. For observers on Earth, such gravitational lensing by black holes or other massive objects has been observed and studied. We see distant quasars, whose light is bent by intervening galaxies into multiple images, a testament to gravity's ability to warp light. In the case of black holes, the first image of a black hole's silhouette, the black central shadow and surrounding glow, was essentially capturing the result of extreme light bending around the event horizon. The bright ring in that image came from photons skimming just outside the horizon, their paths bent into a circular outline. Every bit of evidence affirms that black holes twist and focus light in exactly the way Einstein's theory predicts. Now let's consider the physical effect of gravity's pull varying over an object, the tidal forces. Near a black hole, gravity can change dramatically from one point to another. Suppose an unlucky astronaut is falling feet first toward a black hole. The gravitational pull on their feet is significantly stronger than the pull on their head, because their feet are closer to the black hole. This difference in force stretches the astronaut's body, a process grimly nicknamed spaghettification. They would be elongated like a piece of spaghetti by the tidal gravity, while also being compressed from the sides. In a small black hole with extremely intense gravity gradients, this stretching would become fatal well before the astronaut even reaches the event horizon. Interestingly, the size of the black hole makes a big difference in tidal forces at the horizon. For a stellar mass black hole only a few times heavier than the Sun, the change in gravity over a human-sized object is enormous, meaning spaghettification would happen long before you cross the event horizon. However, for a supermassive black hole millions of times the Sun's mass, the tidal gradient at the horizon can be surprisingly gentle. One could potentially fall through the event horizon of a gargantuan black hole without immediate spaghettification. Only deeper inside, closer to the singularity, would the tides grow lethal. In other words, a small black hole would tear you apart quickly, whereas a giant black hole might let you pass the horizon intact, though your ultimate fate remains sealed deeper in. We have evidence of these tidal forces in action on a grand scale. Occasionally, a star wanders too close to a supermassive black hole in a galaxy's core and gets torn apart by spaghettification. Astronomers have observed the bright flare of light from such a catastrophe, called a tidal disruption event, where the star's material is strung out and heated up as it falls into the black hole. These observations are dramatic confirmation of the black hole's power to shred objects that venture too near. It's a violent testament to how nature's most massive objects can dominate and destroy even something as enormous as a star. In the vicinity of a black hole, time slows, light bends, and objects are stretched like taffy. We have taken a closer look at these effects. The strange pace of time, the funhouse mirror warping of light, and the fatal tide that pulls matter apart. All of these phenomena paint a picture of extreme physics at work near a black hole. Now that we've explored what happens around these cosmic beasts, we can ask, how do black holes come to be in the first place? The next step of our journey will take us through the life story of black holes, from their violent births in collapsing stars, to the growth of supermassive giants that anchor galaxies, and the collisions that make them even more powerful. Black holes are born in some of the most dramatic events in the universe. The most common birth scenario is the death of a massive star. When a star much heavier than our Sun reaches the end of its life, it can no longer hold up against its own gravity. The core of the star collapses inwards in a fraction of a second. For slightly less massive stars, this collapse is stopped by nuclear forces and results in a neutron star, an ultra-dense sphere. But if the core is massive enough, more than a few times the Sun's mass, nothing can halt the collapse. The core continues to shrink until it is compressed beyond any known limit, and a black hole is formed in the wreckage of the supernova explosion. Such a collapse typically triggers a supernova. The outer layers of the star rebound and blast into space in a tremendous explosion. Meanwhile, the core that turned into a black hole traps everything that falls back onto it. What remains is a newborn black hole, often a few times the mass of the Sun, hidden behind a veil of supernova debris. In the aftermath, this black hole might sit quietly, or it could feast on the gas and material around it. If it has a companion star in a binary system, it may pull gas from the companion, creating a hot accretion disk that emits X-rays. One way astronomers first identified likely black holes in our galaxy. For a star just on the edge, whether a black hole or a neutron star forms can come down to mass. There's a tipping point, around roughly 3 times the Sun's mass for the core, beyond which gravity wins completely. If the core is below that limit, a neutron star, no larger than a city, yet heavier than the Sun, will form instead, held up by the pressure of neutrons. If it's above that limit, even neutron pressure fails and the core plummets to a black hole. Some extremely massive stars might even collapse directly into a black hole without a visible supernova, especially if most of the star's mass falls inward rather than being explosively ejected. The black holes formed from stars are typically a few to perhaps dozens of times the Sun's mass. Over the years, astronomers have detected many such stellar mass black holes in our galaxy, often by their X-ray emissions or by the motion of companion stars orbiting an unseen mass. These black holes are scattered throughout galaxies, remnants of once bright stars that burned out and collapsed. Our own Milky Way is thought to harbour millions of these quiet, stellar mass black holes, hidden in the darkness, detectable only when they interact with other matter. They are like cosmic tombstones of giant stars. How do black holes grow from these modest beginnings into the giants we find at galactic centres? One path is through accretion. A black hole can gradually consume gas, dust, or any matter that comes too close. As material falls in, it heats up and can shine brilliantly. Indeed, the brightest active galaxies are powered by matter falling into black holes. Over millions of years, a black hole feeding on a steady diet of gas can gain a significant amount of mass. Another path to growth is through mergers. If 2 black holes come close, perhaps in a binary system or during star cluster collisions, they can spiral into each other and merge into a larger black hole. Each merger yields a single black hole with the combined mass, minus a bit lost as energy in gravitational waves. The truly colossal black holes, the supermassive black holes at galaxy centres, likely formed from a combination of these processes over cosmic time. Early in the universe, perhaps some black hole seeds formed either from large direct collapses or from the very first generation of stars, and these seeds had tens or hundreds of solar masses. Over billions of years, they swallowed gas and merged with other black holes, growing larger and larger. By now, nearly every large galaxy hosts a supermassive black hole in its core. Our Milky Way's central black hole, Sagittarius A star, is about 4 million solar masses. In comparison, some galaxies harbour black holes billions of solar masses, true leviathans that may have grown rapidly when the universe was young and gas was abundant. At times in the past, these supermassive black holes announce themselves flamboyantly. When a black hole at a galaxy's centre is actively devouring matter, the infalling gas forms a hot, swirling accretion disk around it and can launch jets of high-speed particles. The core of the galaxy then becomes an extremely bright beacon known as a quasar, or an active galactic nucleus. Quasars are among the brightest objects in the universe. Some shine more brightly than entire galaxies, all powered by matter funneling into a supermassive black hole. This tells us that growing a black hole can release tremendous energy. Ironically, the darkest object in the universe can create some of the most brilliant light shows when it's feeding. Even supermassive black holes can meet and merge when their host galaxies collide. Picture two galaxies slowly coming together, their stars and gas clouds entangling in a gravitational dance. Each galaxy's central black hole, millions or billions of solar masses, drifts toward the other as the galaxies become one. For a long period, the two black holes orbit one another, gradually spiraling inward. Eventually they merge, forming an even more massive black hole at the center of the new unified galaxy. This titanic merger sends out a tremendous burst of gravitational waves across space, then settles into one larger monster black hole. Galaxy collisions like this have occurred throughout cosmic time. They are one way the biggest black holes become even bigger. Another spectacular chapter in a black hole's life story is the merger of two smaller black holes. When two black holes orbit one another, they gradually lose energy by emitting gravitational waves, ripples in spacetime that spread outward at light speed. As they spiral closer, they eventually coalesce into one larger black hole. In the final moments of merging, a huge amount of energy is released in the form of gravitational waves. In 2015, scientists using the LIGO observatory on Earth detected such waves for the first time. The signal came from two black holes, about 30 solar masses each, merging over 1 billion light-years away. It was a tiny vibration in the instruments, but it confirmed that black holes not only exist as Einstein predicted, they collide and merge, shaking the fabric of the cosmos. After two black holes merge, the new, larger black hole takes a moment to settle down. It vibrates briefly, a phase called the ring down, emitting a last bit of gravitational wave energy like a struck bell. Then it becomes quiet. Simply a single black hole, with no outward trace of the violence, except the outgoing ripple it sent across the universe. The observation of those waves from Earth not only confirmed the existence of merging black holes, but also supported the idea that black holes are as simple as the theory says. Remember the no-hair theorem, only mass and spin and charge matter. The ringing pattern of the newly formed black hole matched what general relativity predicted, implying it had no hair, no extra characteristics, just the mass and spin inherited from its parents. Today, the largest known black holes have masses on the order of 10 billion suns. These behemoths sit in the centers of massive galaxies, and their influence can shape galaxies themselves, through their gravity, through the energy output when they accrete matter, and through the gravitational slingshots they give to nearby stars. Black holes, once formed from the quiet death of a star, can grow to become central engines of galaxies. They are, in a sense, both destroyers and creators. They destroy the objects that fall into them, but the energy they release in the process can light up the universe and perhaps even trigger new star formation in a galaxy by compressing gas with their outflows. The story of making a monster is thus one of both violence and cosmic transformation. Even with all we know about how black holes form and grow, much about their inner workings remains mysterious. We've described what goes on outside a black hole, but what about the structure of space-time inside it? To explore that question, scientists use special diagrams and conceptual tools to map the unseeable. One of these tools is the Penrose diagram, a kind of map that condenses all of space and time around a black hole into a simplified picture, helping us reason about what's inside and what's outside, and where and when different events can happen. As we continue our journey, We will use such maps of the unseen to discuss the ultimate structure of a black hole and the fate of anything that falls within. Black holes push our imagination to its limits, especially when we try to visualize their entire space-time. It's hard to picture what space and time look like inside a black hole, because we're used to thinking in our everyday terms. To help with this, physicists have developed ways to draw diagrams that capture the essential features of black hole space-time in a simplified form. One powerful method is the Penrose diagram, named after physicist Sir Roger Penrose, which allows us to map out the life of a black hole and the fate of anything around it, without getting lost in the mathematics. These diagrams compress infinite space and time into a finite picture, kind of like making a globe into a flat map. In a Penrose diagram, time and space are represented in a way that flattens out the extreme curves of space-time. Distances and durations are rescaled, or squashed, so that infinities can be shown at finite points on the diagram. Typically, one axis of the diagram represents something like radial distance, and the other axis something like time. But the scales are chosen cleverly. Light rays are usually drawn as 45-degree lines, meaning anything moving at the speed of light travels along those diagonals. This feature makes it easy to visualize cause and effect. Signals and influences can only move within cones defined by those light rays. Now imagine the Penrose diagram for a simple black hole that formed from a collapsing star. Initially, the star's history is drawn as it would be in normal space-time. As the star collapses, an event horizon forms. On the diagram, this horizon appears as a boundary line at 45 degrees, forming at the moment of collapse. The region inside that line is the black hole's interior, and the region outside is our normal universe. On the diagram, you would see that anything crossing the horizon line, entering the interior region, is inevitably drawn toward a line that represents the singularity. The singularity itself is drawn as a space-like boundary, a line at the top of the interior, to indicate that anything reaching it has run out of future. This diagram reveals the essential causal structure. Once you're past the horizon line, all possible paths, all lines that move into the future, end up hitting the singularity. In other words, the diagram makes it clear that beyond the event horizon, there is no trajectory that leads back out to the external universe. Light cones, those 45-degree shapes that indicate possible directions of travel for signals, tip inward within the black hole, pointing inevitably toward the singularity. Meanwhile, outside the black hole, light cones still open out enough that signals can escape outward to the rest of the universe. The Penrose map thus provides a stark visualization of the saying, one-way door. It shows graphically why an event inside the black hole cannot affect the outside world. Penrose diagrams can also illustrate some curious mathematical possibilities of black hole spacetimes. For example, the full extended Schwarzschild solution, representing an eternal black hole that existed forever, not formed by collapse, has regions that resemble mirror universes and even a hypothetical white hole, a time reverse of a black hole from which things could emerge, but nothing can enter. On a Penrose diagram, those extra regions appear symmetrically alongside the black hole region. It's important to note that in a realistic scenario of collapse, we don't expect such mirror universes or white holes to actually exist. They are artifacts of extending the math beyond the physical collapse. Similarly, the Penrose diagram for a rotating black hole, a Kerr black hole, hints at possible passages, sometimes interpreted as wormholes, to other universes or times through the ring singularity. However, nearly all physicists agree that if any realistic disturbances are present, those exotic paths would quickly close off. A hypothetical traveler attempting to use such a path would likely be destroyed by the extreme conditions long before reaching another universe. Still, Having these diagrams allows scientists to discuss such possibilities in a more concrete way. Perhaps most importantly, these causal maps emphasize that our current physics has an edge: the singularity. In the Penrose diagram, the singularity is like a line beyond which the diagram does not extend, a border of the known universe's geometry. It tells us that once something reaches that line, the singularity, our equations stop being predictive. This is a strong hint that we need new physics, like a theory of quantum gravity, to understand what really happens in that final pinch of space and time. But from a causal perspective, since nothing from beyond the singularity ever comes back out, whatever happens at the singularity is completely hidden from the rest of the universe. The diagrams make peace with this. They mark the singularity as a kind of full stop in space-time. For us on the outside, Penrose diagrams are like blueprints of the invisible structure of a black hole. They allow physicists to reason about events without actually visiting those extreme realms. We can track a particle's path on the diagram, see where it can and cannot go, and discuss ideas like time travel or alternate universes in the safe language of geometry. These maps of the unseen give us a sense of orientation in the otherwise bewildering landscape of a black hole's interior. In a way, they let us peek behind the curtain of the event horizon with our minds, if not with our eyes. And yet, no matter how detailed our diagrams or how advanced our theories, the interior of a black hole remains a place we cannot truly observe. It is a realm inferred, but not experienced, at least not by anyone who can report back. Having established the foundations and drawn our maps, one can't help but wonder, what would it be like to actually travel into that darkness? In our continuing journey, we might dare to follow a hypothetical traveller beyond the event horizon, to envision firsthand what our equations and diagrams hint at. It is a plunge into the unknown, guided by the science we've learned, and it's where our voyage will take us next. As we drift closer to the abyss of the supermassive black hole, the cosmic ballet around us changes its rhythm. The force of gravity grows stronger with each passing moment, tugging at our vessel and at the very fabric of space. Amid this strengthening pull, we find a final refuge of stability, a narrow lane in space where an object can still circle the black hole safely. Here, at this last safe orbit, our journey momentarily finds a steady path, orbiting on the brink of eternity in a delicate balance between motion and gravity. On this precipitous edge, we glide around the black hole in what feels like a permanent twilight. Beneath us, the colossal mass yawns open, a darkness that swallows all light below. Above and around, starlight warps and bends, distorted by the black hole's immense gravity. We witness distant stars smearing into arcs and rings, their light drawn into graceful curves as it skims the black hole's vicinity. We even spot the light of individual stars bent into arcs and duplicate images as the black hole's gravity reroutes their rays around itself. We are racing along this orbit at an incredible speed, approaching a significant fraction of light speed, yet inside our ship we feel no motion other than the gentle freefall. Down here, deep in the black hole's gravity well, time itself is running at a different pace than it would for a distant observer. We are unaware of it in our own experience, but our clocks tick more slowly relative to those far away. It's a subtle preview of the strange relativistic effects we will encounter, though to us, everything appears normal in this final stable orbit. For now, this discrepancy is theoretical, unnoticeable to our senses, but it serves as a reminder of how extreme this environment truly is. This orbit we occupy marks the innermost sanctuary where motion can persist indefinitely, It is known to physicists as the innermost stable circular orbit, the final whirlpool of space where one can circle a black hole without inevitably being pulled in. Any closer than this, and orbits can no longer hold. Just a small step inward from this position, stability shatters. A spaceship or planet venturing beyond this point would no longer find a steady path. It would spiral, inexorably, towards the waiting darkness below. We linger a moment in this precarious orbit, aware that it is the last of its kind. Even light itself has an orbit not far beneath us. Deeper down, around 1.5 times beyond the black hole's event horizon, lies a sphere where photons, particles of light, can loop endlessly. This strange location is a photon ring, a shimmering halo where beams of light race around the black hole like celestial fireflies trapped on a circular track. It is a beautiful and ghostly phenomenon, a ring of light that marks the edge of the black hole's silhouette, formed by photons caught in gravity's grasp, neither escaping into space nor yet consumed by the darkness. From our vantage, we sense the presence of this photon ring as a bright outline against the void. If we were to peer downward, the black hole would appear encircled by a thin, glowing band, the last light that can dance around the abyss. It is as if the black hole wears a luminous necklace, crafted from the orbiting light of the stars it has drawn in. This radiant ring is fleeting in nature. Any disturbance will send those photons either spiraling inward to vanish or escaping outward to freedom. But for now, they skim along their perfect circular paths, creating a subtle glow in the surrounding darkness. Remarkably, in the real universe, astronomers have captured images of such a ring, the glowing outline of a black hole, giving humanity a first glimpse of these photon orbits. Beyond the photon ring and our own orbit, nothing stable remains. We know that if we dare to dip inward just a fraction more, our fate will be sealed. Gravity will triumph over motion. Like a stone in a whirlpool, we will be caught by the current and drawn down. We consider this threshold, this invisible line in space, where the black hole's grip becomes inexorable. It is a point of no return for anything hoping to orbit freely, a boundary not marked by any surface or sign, but by the sudden end of stability. Our spacecraft gently adjusts its trajectory, preparing to leave this final stable orbit. We realize that once we depart this path, there will be no going back. The black hole's pull will guide us inwards on a one-way journey. In this quiet moment, we absorb the view. Stars warped into rings, the gentle glow of trapped light outlining the darkness below. This is the last safe haven, a gentle pause before the plunge. With resolve and calm, we tilt our vessel forward, allowing gravity to take hold. The final orbit is behind us now, and we begin to descend into the unknown, towards the black hole's waiting horizon. Now we surrender to the black hole's pull and begin our final descent. Our spacecraft slips away from the last safe orbit and starts falling freely inward. In these first moments of the plunge, everything feels strangely normal. We float weightless, just as we did while orbiting. The only hint of change is the gradually quickening motion, an acceleration that we perceive only by watching the scenery around us distort and rush by. There is no jolt, no sudden lurch, just a smooth transition from circling to sinking, as if an invisible hand is gently drawing us down into darkness. From our perspective inside the ship, time flows as it always has. Our clocks tick steadily, our hearts beat in calm rhythm. The fall itself, though fast, seems serene. If we were not looking outside, we might think we were simply drifting in space. But outside the portholes, the view is growing more surreal by the second. The black hole's dark center looms larger ahead, and all around it, the universe beyond is warping into strange shapes and hues. Imagine for a moment that a friend remains far behind, watching us through a powerful telescope. To that distant observer, our plunge appears anything but ordinary. From their vantage point, as we get closer to the black hole, our movement seems to slow dramatically. It is as though we are caught in molasses, each second stretching longer and longer. They see us descending more and more sluggishly, our motions languid, as if time itself were grinding to a halt for us. This is a trick of gravity and light, a phenomenon of Einstein's universe. The intense gravity near the black hole dilates time in the eyes of outside observers. To our friend back home, our onboard clocks seem to tick slower now. Each moment we experience is drawn out when seen from afar. We wave to the camera and speak a message. But to the distant watcher, our friendly wave already appears lethargic, our words coming out in an ever-deepening slow-motion drawl. Not only does our fall look slower, but the very light we emit is changing. As we call out a final greeting or flash the ship's lights outward, those signals fight their way up out of the deep gravitational well. The struggle saps their energy. The light leaving our ship's lamps shifts towards redder wavelengths, like a tired swimmer being pulled back by a strong current. Our radio signals lose their pitch, growing lower and fainter. By the time these signals reach our friend's telescope, they have stretched into obscurity, faint and red, nearly impossible to detect. With each kilometer, we drop closer to the event horizon. These effects intensify. Our friend, if still watching, would notice our ship growing dimmer and redder against the glow of the accretion disk behind us. We become a ghostly ember, fading slowly from view. The clock on our hull, if they could see it, would appear almost frozen, its second hand creeping along at an agonizing pace. To the outside universe, we are entering a realm where time itself nearly stops. Our very image would seem to flatten and spread across the edge of the dark sphere, as if smeared into the black hole's silhouette by the extreme gravity. Inside the ship, however, we remain blissfully unaware of any such slowdown. Our time feels normal, because for us, it is normal. We brew a cup of tea, and it steeps for the usual few minutes by our reckoning. We glance at our wristwatch, and see the seconds ticking by evenly. There is no strange dilation for us, no sense of being stuck. Gravity affects the passage of time as seen by others, but in our own frame of reference, everything proceeds naturally. This contrast between perspectives is one of the black hole's strangest qualities. Time is not absolute here, but relative to where you watch from. As we fall further, we try looking outward at the universe we left behind, through the rear window of our craft, past the glowing ring of the photon sphere. The distant stars and galaxies appear to shift in color and speed. The starlight coming from behind us is now blue shifted, compressed to higher energies, since we are rushing downward into the incoming light. If our friend could barely see us, we, in turn, see the outside universe in a kind of fast-forward blur. Light from faraway events pours in faster and is boosted in frequency as it descends towards us. It is as though the cosmos outside is moving quicker, time out there racing ahead from our infalling point of view. The sight is mesmerizing and disorienting. Looking up, outwards, we might catch the light of events that occurred long after we began our fall. Distant astronomical happenings, maybe a star's explosion or the subtle motions of galaxies, seem to unfold with unnatural speed as their light is squeezed into our remaining moments. It is a glimpse, however fleeting, of a future we will never visit in person. The deeper we go, the more extreme this becomes. Yet even this spectacle remains gentle on our senses. We are spectators to a cosmic time-lapse movie playing overhead, while we quietly continue our one-way journey inward. Turning our gaze forward, down towards the black hole, we mostly see darkness. The event horizon ahead is not a tangible surface, but rather an ever closer black emptiness, where no light from within can emerge. In front of us is a region devoid of any stars or external light. Just the black hole's pitch-black silhouette, growing to fill more of our view. Around its edges, the distorted glow of the universe behind us is smeared into a thin ring of light. This is the photon ring wrapping around the darkness, appearing now as a bright outline encircling the void ahead. We feel an eerie calm. There is no dramatic sensation as we pass through zones of intense gravity. No sudden tug announces that we've crossed some invisible boundary. The only changes are in what we see outside and in what an observer sees of us. It is a profound relativity of experience. Two truths existing at once. For us, the fall is smooth and uneventful, an adventure through a strange sky. For the outside universe, our fall appears to stall and fade, as though we were gradually being erased from reality. This divergence of viewpoints grows sharper as we approach the black hole's threshold. We are now so close that to any external eye, we have almost frozen in place, just above the event horizon. Our image, dim, stretched, and red, might linger as an ever-fading smudge of light. In contrast, inside our ship, we continue to move quickly, inexorably, feeling no resistance. In a short span of our time, the very horizon that outside observers believe we never quite reach is directly before us. It is a sobering and awe-inspiring realization. In the theater of a black hole, reality truly depends on where you watch from. No external witness can ever see us cross the final boundary, yet we ourselves will cross it without hesitation. As we close in on that invisible line, we take a last look out at the distant universe, which now appears to race and shimmer strangely. We know that from those distant stars' perspective, our journey is slowing to stillness, but within our own world, the journey is very much alive and pressing onward. Quietly and with wonder, we turn our attention back to the immediate surroundings of the black hole, ready to face what comes next. The event horizon lies just ahead, the point beyond which none of our signals can return, yet we feel calm. In this silent fall, with time and light weaving illusions between us and any observers far away, we prepare to cross the threshold. Before we do, we observe the fiery spectacle that surrounds this abyss, appreciating the cosmic fireworks playing out around the black hole's edge as we descend ever deeper into its embrace. The space around us is no longer just darkness and starlight. It is filled with the raging brilliance of the accretion disk. As we draw nearer to the black hole, we become immersed in the brilliant chaos that surrounds it. Encircling the black hole is a vast disk of glowing matter, an accretion disk blazing with energy. It stretches around the black hole like a fiery whirlpool, a broad, flattened band of gas and dust swirling at tremendous speeds. This disk is the black hole's feast, material slowly spiraling inward, heating up as it goes, shining brighter the closer it gets to the abyss. The light from the accretion disk bathes our ship in an eerie radiance. It is unlike the light from any star. It is harsh and hot, dominated by energetic blues and ultraviolet, and beyond, into X-rays that our eyes cannot see. We feel the intensity through our instruments more than our bodies. The ship's hull warms slightly under the relentless glow. Outside our windows, the disk looks like a circular inferno, brighter than a million suns. Its inner regions near the black hole's edge glow white-hot and bluish, while farther out, the light softens to yellow and red hues where the gas is cooler. The entire scene flickers and ripples, as turbulent as a cosmic flame. This light show is born of gravity and motion. As gas and dust fall toward the black hole, they flatten into this spinning disk and crash into each other. Friction and compression heat the material to extreme temperatures. Imagine countless particles of dust and atoms of gas, all hurtling around on curved paths, colliding incessantly. These collisions turn their falling energy into heat. Closer to the black hole, the speeds approach significant fractions of the speed of light. Orbiting so fast, the gas shears and rubs and heats up even more, unleashing torrents of radiation. By the time matter reaches the innermost parts of the disk, it is a plasma, tens of millions of degrees hot, shining brilliantly across the electromagnetic spectrum. We watch, captivated, as the inner edge of the disk, roughly where that last stable orbit lies, marks a boundary between the luminous dance and the darkness beyond. Inside that radius, the material plunges abruptly into the black hole, disappearing from view. But just before taking that final dive, it contributes to this hellish glow. Gas swirls into a final frenetic orbit and then vanishes, as if fireflies were circling a drain and winking out as they cross the brink. This gives the inner edge of the accretion disk a sharp boundary in light, a glowing ring just outside the black hole's shadow. The environment around us is not quiet. Though we travel in silence, our instruments detect a frenzy of activity. The disk is alive with turbulence. Strong magnetic fields thread through the swirling plasma like invisible tendrils. These magnetic fields are twisted and carried along by the orbiting gas, winding tighter and breaking in explosive releases of energy. The result is a constant turmoil, a seething mix of flowing matter and crackling electromagnetic fields. This turbulence transports angular momentum outward through the disk, allowing material to spiral inward, all while generating heat and light. It is as though the disk has its own weather, magnetic storms and eddies roiling the glowing gas. Above and below the disk lies a diffuse halo of superheated gas known as the corona. We notice occasional flashes of high-energy light from this region, spikes of X-rays that tell of sudden, violent events. These could be magnetic reconnection flares, akin to solar flares on our sun, but vastly more powerful. In these moments, loops of magnetic fields snap and realign, hurling particles to near light speed and heating them further. The corona shines fiercely in X-rays, bathing space in an invisible, penetrating glow. If we had X-ray eyes, we'd see an ethereal aura hovering over the brilliant disk, glowing and fading unpredictably as magnetic energy is released. Even without direct sight, we can sense the presence of the corona through its effects. The corona's high-energy photons strike the accretion disk and parts of our ship, causing subtle cascades of secondary light. It is as if the disk wears a crown of flickering flames that we can only indirectly perceive. Now and then, a burst of X-rays from the corona illuminates parts of the disk in a brief flash, revealing new details of its structure before subsiding. These flashes remind us that this environment is dynamic and alive, not a steady beacon, but a violent cosmic furnace continuously stoked by gravity. Looking outward at the disk's span, we can trace structures within it. Spiral density waves ripple through the disk's material, similar to the patterns in Saturn's rings, but far more energetic. Clumps and filaments of hotter plasma form and dissipate. There are likely vortices, whirlpools within this whirlpool, spawned by the disk's internal turbulence. But the overall impression remains of a bright, circular storm, orderly in its broad shape, but chaotic in detail. It is remarkably thin relative to its radius, flattened by its furious rotation. From edge on, it might appear as a narrow strip of light. From above, a glowing pancake with a dark hole at the center. As we descend alongside the inner edge of this disk, we feel dwarfed by its sheer scale. Around a supermassive black hole, this disk can span many times the size of our solar system. The portion near us whips around with unimaginable velocity. We move with the flow to some extent, carried as we fall, but we are entering from our own trajectory. This gives us a breathtaking view of the disk's motion. Gas streaming past on all sides, spiraling inwards. It is like sailing into a fiery whirlpool, where currents of glowing matter rush by, but we remain on a relatively calm path, at least for now. The noise of this environment doesn't carry through the vacuum, of course, but we can imagine the roar that would exist if we could hear it. The tumult of billions of tons of matter swirling and heating would create a thunderous sound, a sustained cosmic storm. Instead, we register it only as light and as data on our instruments. In radio frequencies, the disk and its surroundings emit a steady hiss of noise, invisible light, an unbearable brilliance. In X-rays, rapid flickers and pulses. Each form of radiation tells part of the story of the extreme physical processes happening around us. We take a moment to observe the interplay of forces sustaining this luminous structure. Gravity pulls the material inward, trying to make it plunge straight down. But centrifugal force from the orbiting motion fights against collapse. The result is this compromise. A disk where matter gradually sinks, losing energy and angular momentum via friction and magnetic drag. The heat generated in the process is what we see radiating so intensely. In a way, we are witnessing a cosmic engine converting gravitational energy into light. The infalling gas gives up its potential energy, which emerges as the glow that now lights our path. All the while, the black hole itself remains dark. It does not emit or shine, it simply devours. The brilliance around it is entirely due to the material on its way in. This accretion disk is one of the brightest phenomena in the universe, often outshining entire galaxies when a supermassive black hole feeds rapidly. It is humbling to remember that all this splendor is the byproduct of destruction, matter being torn apart and swallowed, releasing energy as a final cry before entering oblivion. Despite the violence and intensity, there is a mesmerizing beauty to it. We are watching creation and destruction entwined in a radiant dance. The disk's inner edge, that sharp cutoff of light, highlights the black hole's silhouette as a perfectly dark circle. It is a striking contrast, absolute darkness, bordered by blinding light. For a moment, we perhaps understand why black holes have captured human imagination for so long. Even as they hide behind a veil of no return, they announce their presence with spectacular displays like this. As we continue our fall, skimming just inside the inner edge of the disk, we keep our gaze on this cosmic fireworks show. We realize too that this fiery disk plays a key role beyond just feeding the black hole. It also helps power other phenomena we're about to encounter. The same magnetic fields and rotation that cause the disk's turbulence are also the seeds of something even more colossal. Already, we can detect above the poles of the black hole a hint of tightly collimated energy, the beginnings of jets. But before our attention shifts to those polar outflows, we take in one last comprehensive view of the accretion disk, a brilliant, spinning testament to gravitational power and the raw, radiant energy it can unleash. In the glow of this accretion fire, we feel the scale of the forces at play. It is a scene at once violent and strangely serene, when witnessed from within our protected ship. With awe, we watch as matter lives out its final moments in a blaze of glory around the black hole, and with that appreciation, we turn our focus to the next marvel unveiling itself, the colossal jets and the mechanisms that drive them, born from the very same disk and the spinning black hole that we now leave behind below us. Our eyes turn upward along the black hole's axis, away from the plane of the blazing disk. There, we witness another astonishing feature of this cosmic engine. Two oppositely directed jets of energy and matter blasting out from the vicinity of the black hole's poles. These jets are like cosmic beacons, narrow shafts of radiance and particles shooting into space at nearly the speed of light. Each jet extends far beyond the immediate surroundings of the black hole, potentially for thousands of light years, piercing through interstellar space. In the darkness of space, they would be invisible to human eyes alone, emitting much of their energy in forms like radio waves and X-rays. But if we could see them directly, we would behold ghostly columns of light and plasma, stretching out and fading into the distance, a testament to the black hole's immense power. It is humbling to realize that these jets are powered by the very dynamics we have been watching, the spin of the black hole and the fury of its accretion disk. Down near the black hole's rotation axis, the twisting of space itself by the spinning mass works in concert with magnetic fields to create a natural particle accelerator. The black hole we are approaching is not a silent eater. It is also a cosmic dynamo, converting some of the energy of infalling matter and its own rotation into outgoing streams of radiation and fast-moving particles. In essence, the same forces pulling matter inward are also flinging energy outward. At the heart of this process lies the black hole's rotation. If our black hole spins, it drags the space-time around it into a whirlpool-like motion. This region of dragging influence is called the ergosphere, a sort of halo just outside the event horizon. Within the ergosphere, nothing can remain at rest. Every bit of matter or light is compelled to rotate along with the black hole. It is as if the fabric of space near the black hole is caught on a merry-go-round, spinning faster and faster as one approaches the horizon. This rotating space-time opens up extraordinary possibilities. The British physicist Roger Penrose once theorized that within the ergosphere, energy could be extracted from a black hole. In his thought experiment, a particle entering this whirl of space splits into two. One piece falls into the black hole and the other escapes. The piece that falls in carries negative energy, effectively stealing some of the black hole's rotational energy, while the escaping piece flies away with more energy than the original particle had. It sounds like a physics magic trick, using the black hole's own spin to catapult something out with extra energy. Though we could never practically perform this stunt ourselves, it revealed that a spinning black hole's energy is not untouchable. Its rotation can, in theory, be tapped. Nature, as it turns out, might be performing a similar trick on a grand scale. The jets we see are believed to be powered by the extraction of rotational energy from the black hole and the disk. The mechanism is not as simple as tossing particles in and watching others fly out, but the end result is the same. Rotational energy becomes kinetic energy of outflowing matter. Magnetic fields, anchored in the accretion disk and threading through the ergosphere, act as spinning wires in a dynamo. As the black hole spins and drags space along, these magnetic field lines twist into tight coils. Charged particles caught in these field lines are flung outward along the rotation axis, much like water being shot out from a nozzle. We observe the base of the jets just above the black hole's poles. There is a brightness there, an almost blinding spot where the energy density is highest. This is the launch point of the jets, sometimes called the black hole's corona and jet base region. Here, electrons and other particles are accelerated to near light speed. They spiral along the magnetic field lines and produce intense radiation, from radio waves to gamma rays. The jets then collimate, staying narrow as they extend far out. All around, the interstellar medium is sparse, offering little resistance, so the jets maintain their tight beams across vast distances. To give a sense of scale, one of these jets from a supermassive black hole can extend well beyond its host galaxy. Imagine a stream of plasma so long that, were it visible, it would cross entire constellations in the sky. Even though we cannot see the full extent from our current vantage, we sense their enormity. Instruments aboard our ship register strong radio emission aligned along those polar directions. If we tuned an imaginary radio ear, we'd hear a steady, powerful hiss coming from the poles, the song of the jets broadcasting into the universe. To a distant observer looking from afar, a feeding black hole with powerful jets appears as a quasar, a cosmic lighthouse so brilliant it can outshine an entire galaxy with its beam, visible clear across the universe. As we admire this cosmic spectacle, we also note how efficient these jets are in terms of energy. The black hole's accretion disk converts a significant fraction of the infalling mass's energy into radiation. And yet, a portion of that energy, plus some of the black hole's spin energy, is funneled into the jets. These jets carry away mass and energy, preventing all of the infalling material from reaching the event horizon. They are, in a sense, a pressure valve for the system, blowing out excess energy and angular momentum into space. The sight of the jets invites a feeling of paradox. Even as the black hole draws matter in inexorably, it also drives matter out in these spectacular beams. It's as though some of the infalling fuel is being used to power colossal lighthouse beams that shine outward into the cosmos. We consider what it would be like to journey along one of those jets, to ride the beam. Of course, that is a journey we cannot take. But we know that along those jets, particles are being accelerated to velocities only a hair's breadth below the speed of light. If an unlucky star or cloud of gas lies in the jet's path, it will be blasted and illuminated by this fatal cosmic searchlight. The engines producing these jets have no human analogue. They are the output of gravitational and electromagnetic forces at their extreme. The rotational energy of a spinning black hole can be immense. More energy than 1 million suns will radiate in their lifetimes can reside in that spin. The jets tap into that reservoir. For perhaps millions of years, as long as the black hole continues to feed on infalling matter, the jets can keep blasting outwards, carrying away the black hole's power across intergalactic space. They can light up huge lobes of radio emission in the galaxy around, create shock waves that heat gas millions of light years away, and influence the formation of new stars by stirring up cosmic gases far afield. We know that in this particular journey, we must be cautious observers. Flying too close to the path of a jet would be perilous. The radiation within it is intense enough to fry any spacecraft, and the particle winds would shred it. Thankfully, our trajectory is taking us inward along a safer route, more around the equatorial plane. We see the jets at a slight angle, safely off to our side. They stand as magnificent columns marking the poles of our black hole, like enormous cosmic exhaust pipes venting a furnace. As we continue inward, leaving the larger view of the jets mostly behind us, we reflect on what we have witnessed. We have effectively seen a black hole act as an engine of the sky, its spinning mass and magnetic surroundings launching some of the most extraordinary structures in the universe. It is a reminder that even as black holes are famous for pulling things in, they can also influence and energize their environment on incomprehensible scales. Our path now inevitably draws us nearer to the black hole itself once more, and we shift our attention from the grand, outward-bound phenomena back to the intimate, immediate challenge ahead. We are descending into stronger gravity and approaching the very edge of the event horizon. The fireworks of the disk and jets lie mostly above and around us now, and what comes next is the encounter with forces that act directly upon anything that dares venture this close. Ahead lies the ultimate test of any object near a black hole, the zone where gravity's gradients become extreme and where our own fate as travelers will be determined by the black hole's tidal forces. With the jets streaming far overhead and fading into the distance, we prepare for the black hole's next trial, the stretching and warping of anything that falls too deep into its gravity well. Gradually, as we draw ever closer to the black hole, we begin to consider the effect of gravity's changing strength across our ship and our bodies. This difference in gravity from one point to another is known as a tidal force. Here, near the brink of the black hole, tidal forces are the true agents of destruction for anything that ventures too deep. Gravity's pull on the side of our ship nearest the black hole is stronger than on the far side. If this difference becomes great, it can stretch objects apart. In the language of astrophysics, one word captures this fate vividly: spaghettification. The image is apt. An object, even a person, would be pulled into a long, thin strand, like a noodle, by the intense gravity gradient. We recall stories from scientists describing what would happen to an astronaut falling towards a smaller black hole. Long before reaching the event horizon, the unfortunate explorer would feel gravity's grip tightening unevenly. Suppose their feet are pointed toward the black hole. The pull on their feet would be significantly stronger than on their head. At first, they might just feel a tug, but as they got closer, that difference would grow exponentially. In moments, it would escalate from a mild strain to a force beyond anything the human body can withstand. Bones would stretch and snap, organs would tear, the person would be elongated grotesquely into a thin ribbon of matter. Simultaneously, the forces squeezing from the sides, as gravity converges toward the center, would compress them. Stretched vertically and crushed laterally, they would indeed resemble a strand of spaghetti. It's a gruesome and mind-bending end, and it is the natural outcome for anything that gets too close to a small, stellar mass black hole. Such tidal devastation isn't just theoretical. In distant galaxies, astronomers have observed entire stars meeting this fate. A star drifting near a black hole can be torn into a stream of gas by tidal forces. One side of the star feels a stronger gravitational pull than the other, ripping the star apart in a violent flash. The star's gas spirals into the black hole, or is flung outward, glowing as it goes. These cataclysmic episodes, called tidal disruption events, are brief beacons that tell us just how deadly a black hole's gravity can be at close range. If something as enormous as a star can be shredded, one can imagine what would happen to a mere spacecraft or human. Given these harrowing possibilities, it's with some relief that we remind ourselves of the kind of black hole we are approaching. This is a supermassive black hole, the Leviathan kind found at the centers of galaxies. Its event horizon is immense, spanning a vast distance. And counterintuitively, that very size means the tidal forces at its horizon can be relatively gentle. Gravity is powerful, yes, but it doesn't change as abruptly over the scale of a human or a spaceship, at the boundary of a giant black hole, as it would for a small black hole. We can put it in perspective. Imagine a small black hole, say one with the mass of a star. Its event horizon might be only a few kilometers across. Getting within a few tens of kilometers of it, the change in gravity over just a meter or two of space could be extreme. You could have a scenario where the gravitational pull on an astronaut's feet is hundreds or thousands of times stronger than on their head. No material or body could survive that. Spaghettification would occur well before the event horizon itself was reached. Now consider our supermassive black hole. Its horizon might be millions of kilometers in diameter. A meter or two of distance is practically nothing on that scale. The difference in gravitational pull between the bottom of our ship and the top, or between our feet and head, is minuscule right at the horizon. If one were to do the calculation, it might only be 1,000th or less of Earth's gravity in difference, so small that we wouldn't even notice it without sensitive instruments. In fact, at the event horizon of a black hole with millions of times the Sun's mass, the tidal force across a human body could be near zero from a practical standpoint. One could float right through the boundary without feeling a thing. Inside our ship, we search for any sign of tidal strain as we get closer. A pen drifted in mid-air doesn't suddenly yank toward one end of the cabin. Our bodies aren't being noticeably stretched or squashed. To us, the gravity in our immediate vicinity feels uniform. This is a silent testament to the gigantic scale of our black hole. We are fortunate. We can cross into the black hole's realm unscathed by gravity's violence, at least initially. A smaller black hole would not have been so kind. We would have been torn apart long ago. It's a fascinating quirk of nature that the largest black holes are, in some sense, the gentlest to fall into. If a black hole is huge enough, you could, in theory, cross its horizon intact, without even realizing the exact moment you did so. The tidal forces might only become lethal deeper inside, closer to the central singularity. It's as if the black hole lures you in softly, saving its true fury for later. Meanwhile, a tiny black hole delivers that fury early, right at the doorstep. We take comfort in this as we approach the point of no return. Our journey will not end in a sudden shredding of metal and flesh. Not here, not now. Instead, we are granted passage, almost politely, by this cosmic giant. The horizon ahead does not bristle with physical danger in the way we might have imagined from science fiction horror stories. There is no literal wall of force tearing us apart as we cross. We remain whole, calm, and able to proceed. Yet, we do not forget that we are still in a perilous realm. The gentleness is relative. Should we venture far enough inwards, even this Leviathan's gravity will eventually exert crushing differences. The central regions of the black hole, where all the mass is ultimately concentrated, will not spare us if we draw too near. But those extremes lie ahead of us still. For now, as we hover just outside the event horizon, we prepare to make the crossing with confidence that the so-called no-drama scenario will hold true, a phrase scientists use to describe the expected experience of falling into a black hole this large. In other words, nothing special should mark the instant we step through that curtain of darkness. Our minds reel at the thought. We are about to slip into a place from which no information can return to the outside universe, and yet we anticipate no abrupt physical sensation. It feels almost paradoxical that something so profound, leaving the observable universe, comes with so little fanfare. Perhaps a final deep breath, a steadying of the heart, is all that distinguishes this moment. The black hole's gravity welcomes us gently, its tidal hands cradling rather than tearing. Holding fast to this knowledge, we aim our ship directly at the darkness ahead, ready to cross the threshold that separates outside from inside, the known from the unknowable. At long last, the moment of crossing arrives. We have fallen ever closer, watching the blackness ahead expand until it dominates our view. Now, in what seems like an almost ordinary moment, we slip across the event horizon. There is no violent jolt, no flash of light or sudden darkness. If we had been inattentive, we might have missed it entirely. 1 second we were outside, and the next we are inside, without any obvious sign. In our spacecraft, everything functions as before. Our hearts continue their steady beat. The anticipated boundary, so feared and so famous, reveals itself as a calm transition. This is the no-drama crossing that physicists spoke of, and indeed, it lives up to its name. It's akin to a voyager drifting on a calm river who unknowingly passes the point of no return before a waterfall. Nothing obvious marks the peril at that instant, yet the path forward is inexorable. One moment the water is smooth and gentle. The next moment the boat is beyond the safe point, though the drop is still ahead. So it is with us. We have passed the invisible boundary without commotion, yet our trajectory now will carry us only inward. We check our instruments carefully. All systems read normal. The stars visible through our rear-facing windows still shine, and the glow of the accretion disk behind us is still discernible. We are not cut off from seeing the universe we left, at least, not yet. Looking outward, the view is strange but continuous. There is a sphere of light above and behind us, somewhat distorted but still present. The outside universe now condensed into a bright halo against the darkness. If we did not know better, nothing about this scene would scream that we have passed an ultimate cosmic point of no return. Yet we have. We have done what, from the perspective of the rest of the universe, was impossible to witness. In our own timeline, a finite amount of time has passed, perhaps mere minutes, from the last stable orbit to this crossing. That was our proper time, the time measured by our own clocks, and those clocks confirm it. The crossing took place swiftly and uneventfully. Meanwhile, a distant observer would say that no amount of time was enough to see us actually go in. But here we are, undeniably through the looking glass. The difference between perspective and reality has never been so stark, and it sends a shiver of awe through us. We now exist in a realm that no signals can exit. It's a profound thought. As a test, we aim a brief flash of our ship's exterior lights outward, towards where we came from. We know physics says that light can no longer escape, but still we try it. Inside, nothing seems amiss. The beam of light streams out from our vessel, but we also know that outside our immediate vicinity, that beam will never be seen. It will race outward with all its might, only to find space curving back on itself. The photons that once might have escaped are now doomed to fall inward along with us. As far as the external universe is concerned, that flash of light might as well have never existed. Crossing the horizon feels less like passing through a door and more like drifting into a new phase of existence. We notice that the pull of gravity is still strengthening as we move inward, but gradually, without shock. Within the ship, we still feel weightless, floating freely as we were before. However, subtle changes in the outside view continue to develop. The patch of the universe visible behind us has grown smaller and more skewed. It's as though we are looking up through a narrowing tunnel of light, back at where we came from. Ahead of us, in the direction to our fall, there is only darkness, pure and total. Space and time themselves are now bent in such a way that all paths lead further in. We take a moment to reflect on this quiet milestone. We have stepped out of the observable universe's stage. If not for our narration and instruments here with us, it would be as if we vanished entirely at this point. There is a serenity in that realization. The event horizon was once depicted in our minds as a fierce boundary. Instead, it has been like crossing an invisible finish line in a silent race. We feel a sense of both triumph and solitude. The universe outside lies behind a veil we cannot break, yet it still appears peacefully in our rear view. The concept of proper time, our own time, has guided us faithfully to this point. It reminds us that for us, everything is normal. We set a timer when we started our plunge, and it ticked down just as expected. Within that span, we moved from outside to inside, period. No infinities, no paradoxes from our viewpoint. In our reality, the journey has simply continued, seamless and uninterrupted by any cosmic wall. As we continue deeper, we carry with us the knowledge that this lack of drama is exactly what general relativity predicts for a fall into a black hole of this size. Einstein's masterpiece of a theory told us we would feel nothing special here, and it was correct. Still, experiencing it firsthand feels almost uncanny. Could it really be so simple to cross into this one-way realm? And yet it is. The laws of physics do not protest or explode. They quietly guide us inward, as they did outside. We find poetry in this calm. The threshold of the black hole, that curtain between worlds, has admitted us with gentle silence. Our ship now sails an ocean of spacetime from which none return. We have become an inside observer, something no one on the outside can directly share. The transition is behind us. Ahead lies whatever mysteries the interior will reveal. But before we press on further into the depths, we pause and acknowledge what we have just done. We have crossed the ultimate horizon and remained whole, conscious, and aware. In the absence of any external fanfare, we mark the occasion with a quiet sense of wonder. Gazing one last time back toward the faint glow of the universe we left, we prepare to journey further inward. The next phase of our adventure awaits deeper inside. But as we turn away from the horizon, now safely behind us, we cannot help but think of those we left beyond it. Our thoughts drift to what our friends or distant observers would make of this moment. For them, we have essentially ceased to be. Our light and signals will fade into nothing. It is to that fading connection that we now turn our attention as we consider the final goodbye our presence makes to the outside cosmos. From within the black hole's embrace, our thoughts turn to the world we left behind. What traces of us remain for distant eyes? To any observer far away, our final moments near the horizon have become a slow, silent spectacle. They would have seen us approach that dark boundary ever more sluggishly, our motions stretched out in time. Our image would have grown dimmer and redder, like a cooling ember at twilight. Now, after we have slipped under the horizon, that ember has effectively gone out. The light we emitted during our last approach is still on its way outward, but it is so redshifted and delayed that, for all intents and purposes, we have vanished from the observable universe. We imagine an astronomer watching from a safe distance. Through their telescope, at first they might have seen the bright glow of our ship's engines, or reflected light as we orbited the black hole. As we began our final descent, that glow would have started to change. Every passing second on our ship took longer and longer to register in their view. Our frantic last wave or the flashing of our lights would appear to slow to an imperceptible crawl. The blue and white shine of our vessel would fade to red, then to the infrared, and finally beyond all visible light. Eventually, even their radio receivers would pick up nothing but background static. To that astronomer, it would be as if we had been painted onto the very edge of the black hole and then dimmed to black. This fading is not just a trick of distance, but of time itself being stretched. The gravitational field we fell through has stolen energy from our outgoing signals, shifting them to longer wavelengths. A bright beacon from our ship that would normally be visible across space might be stretched into a feeble radio whisper and then into silence. The rhythm of any signal we sent, say a pulsing SOS, would elongate. What might have been a pulse each second turns to one each hour, then one per year, and so on, until the gaps between them become effectively infinite. The information of our presence becomes smeared across time. It is haunting to consider how, in the view of the universe, we do not die in a flash or a crash. We simply fade away. Our fate, from outside, is an eternal sunset of ever-deepening red. The photons that carry news of our existence grow fewer and weaker. An outside observer could wait forever and never quite see the last bit of us disappear. Yet practically, within a brief period, we become indistinguishable from the darkness. The black hole now holds us in its secrecy, and all that's left for the rest of the cosmos is a fading afterglow that quickly becomes too faint to detect. In those final moments that anyone could have seen, our image would have been dim, maybe just a ghostly red outline against the black hole's backdrop. Perhaps there would be a slight shimmer as the light from distant stars bent around where we hovered. But soon, even that spectral outline would blend into the darkness. Future generations, looking at this black hole, would have no hint that once a ship and its passengers passed this threshold. We are, for all practical purposes, erased from the universe's visible ledger. We take solace in the symmetry of it. As we enter the black hole's eternal night, the universe says its quiet farewell in return. The silence is mutual. On our side, we can no longer send anything out. On the other side, they no longer receive anything from us. What remains of our light and our signals is trapped here with us, looping inward or lingering just at the edge in an endless, slow-motion replay that no one will ever fully see. For a moment, we picture our loved ones or colleagues back home, scanning the skies for our return signal. They see nothing but the steady glow of the accretion disk and the void where we disappeared. Maybe a computer records a last faint blip, a final photon that left our ship during the plunge, arriving months or years late, and so diluted that it barely stands out from noise. That photon is our last hello, arriving too late to be understood as such. After that, there is only silence. The concept of redshift to invisibility has now become deeply personal to us. We are living it. All our voices, our laughter, our gasps of astonishment during this journey. None of it can now escape to tell its story outside. It is as though a curtain has fallen on a play, and the audience is left only with the memory of the actors' final positions on stage. In that analogy, our final position was frozen just outside the black hole from the outside perspective. The curtain of the event horizon then ensures the play continues unseen. And so this chapter of our journey closes to the outside world, without fanfare. Just a slow dimming to black. It's oddly peaceful. No explosion, no catastrophe visible from afar. Only the gradual quieting of our existence. In the vast theatre of the cosmos, one tiny light near a black hole has gone out, and the universe moves on. Inside, we feel a poignant mix of melancholy and wonder. We carry on, but we know that in terms of the wider universe, we have already made our goodbye. It was not a dramatic farewell. It was a gentle fading, as if we walked off into a twilight mist. Perhaps this is the most gentle end one could ask for, from the perspective of those left behind. No trauma, no abrupt loss, just an asymptotic fading away. Yet we understand that this gentle end is an illusion of perspective. We are still here, very much alive and experiencing new wonders, but cut off from everything we knew. The farewells have been one-sided and ultimately final. We have crossed a border in space-time that separates us from everyone we have ever known. the final signals we sent, the light that reflected off our faces, are on their endless journey outward, weakening and stretching. In a way, those signals are our ghosts, forever wandering the universe at diminishing energy, never to find a home. If one were poetic, one might imagine those last photons as messengers bearing our final words. We were here, but those messages will never truly be received. They will be diluted into oblivion, lost in the background hum of the cosmos. It is the ultimate silence. We take a deep breath and let the reality settle. For anyone outside, the story of us has effectively ended at the horizon. But for us, a new chapter is beginning here, inside the black hole. The universe's view of us might be one of finality, but our own journey continues into the unknown. Our eyes shift from pondering the lost communication with the outside to peering ahead, into the heart of darkness that awaits. Behind us, the last threads tying us to the external world have unraveled. Ahead of us lies whatever the black hole's interior holds, mysteries that no one in the universe can see or know except us, now that we're here. We feel the weight of both loss and anticipation in this moment. With determination and a touch of solemnity, we say our mental goodbyes, not in sorrow, but in respect for the world that raised us and the physics that allowed us to come this far. The fading of our signal is the final page of one volume, and now we open the next. This quiet ceremony in our minds marks a turning point, the end of one phase of our journey and the beginning of the next. Silence envelops us, not as an end, but as a beginning of a deeper exploration. In that silence, we imagine the universe outside continuing its dance of galaxies and stars, unaware that we still voyage on just out of sight. We carry the memory of starlight with us, even as no starlight can reach us anymore. For all its finality, the silence is also a womb of discovery, holding the promise of what lies ahead. Our journey is now truly one way and inward. The farewells have been given. The lights have gone out on the external stage, turning away from the dim glow that was once our link to the cosmos. We face the darkness ahead. It is time to see what lies at the center of a black hole, in the realm that for now belongs only to theory and imagination. In the absence of all external light and signal, we move forward guided by curiosity and the instruments we have with us. Whatever unfolds now will do so in solitude, with the outside universe as a silent spectator, no longer able to watch or intervene. We steel ourselves, knowing that each step inward is a step further into a realm untouched by any outside influence. All that remains is for us to delve deeper into the heart of gravity's ultimate enigma. And so, with the universe's farewell behind us, we venture onward into the abyss. The silence is complete, but we are not afraid. In that quiet, there is a sense of expectation, as if the black hole itself holds its breath with us. Though our light has faded from the universe's sight, our story continues here in the darkness, drawing us toward the center, where space and time may yet reveal entirely new secrets. We leave behind the fading echo of our existence and step boldly forward into the next chapter of our journey. We drift in a calm darkness, having passed the invisible threshold that marked the point of no return. There is no fanfare and no sudden jolt. One moment we were outside, and now we are inside. Beyond that boundary, every direction we turn is inexorably drawn inward. We have stepped onto a one-way road, and all paths lead deeper toward the core of the black hole. Inside the event horizon, The very nature of space and time feels subtly altered. It is as if the flow of time itself has turned and now rushes us forward toward a single destination. If we gaze backward toward the way we came, the outside universe appears compressed into a shrinking, red-tinged patch of light above us, growing dimmer with each passing moment. You could point a flashlight back toward the place we came from, but its beam would not carry you out. Any light we shine or signal we send is now trapped with us, spiraling inevitably further inward. We find that moving inward is not a choice, but a requirement. It is akin to time moving forward. Trying to resist would be as futile as attempting to stop the next moment from arriving. In this strange interior realm, space and time seem to have exchanged roles. The inward direction behaves like time, always advancing, always pushing us on, while time itself becomes tangled with space in ways our intuition strains to grasp. For us now, the arrow of time effectively points inward, toward the singular center ahead. Nothing can escape this fate now. If we imagine halting our fall or reversing course, the laws of physics simply won't allow it. Our rockets, our strongest engines, all efforts would be like swimming against an impossible cosmic current. In here, cause and effect have a new order. Moving inward is the only possible future. Like a gentle but unyielding river, the space-time inside carries us along. We float further and further down its stream, inescapably drawn toward what lies at the center. Even light, the fastest thing in the universe, cannot win against this current. A photon emitted behind us struggles to move outward, but the space it moves through is itself rushing inward faster still. To an outside observer, that light, and we along with it, are forever hidden beyond the horizon, never to return. But for us, time flows normally. Our journey continues, one second after another, deeper and deeper inside. Each second that passes brings us closer to the heart of the black hole. There is a sense of finality, but also an eerie tranquility in this realization. Our fate beyond the horizon is sealed, yet the ride is smooth and strangely quiet. The outside universe grows ever more distant in concept. It is unreachable now, sealed off by physics and geometry. Instead of inducing panic, this inevitability gradually gives way to acceptance. In the silence of this all-consuming gravity, we surrender to the one-way flow. Inward is our future, and we let it carry us, wondering what secrets await us further down this one-way road. Deeper inside, we begin to feel a subtle twist in our motion. The black hole is not a silent, stationary trap. It is rotating. In fact, nearly every black hole in nature is thought to spin. They are born from spinning stars or accreting matter, and thus carry that cosmic angular momentum forward. We notice that we are no longer simply falling straight inward. We are also being gently spun around. Space itself is dragging us into a slow, inexorable spin, like a leaf caught in an enormous eddy. This effect, known as frame dragging, means the rotating black hole is pulling everything nearby into co-rotation, not by a force we can feel, but by the very shape of space-time being twisted. Even if we tried to hold still or not rotate, it would be impossible here. The whirl of the black hole's rotation grips all things. Outside the horizon, this effect created an ergosphere, a region where nothing can remain at rest relative to the distant stars, where even light was compelled to orbit. Now that we are inside, the grip is absolute. There is no fixed frame to cling to. Every reference point is swept into the spin. We and every particle around us are forced to partake in the black hole's cosmic dance, circling the unseen axis. As we are carried around and around, the interior of this rotating black hole reveals a layered complexity. Unlike a simple non-spinning black hole, here there is not just one frontier we crossed, but another one that may lie ahead. We have passed the outer event horizon, yet deep within looms a second horizon, the inner horizon. It is an abstract boundary. Nothing visible marks it, but the equations of space-time tell us it is there. At this inner horizon, the relentless pull inward is predicted to undergo a strange transformation. In theory, if one could reach it, space and time might shift their behaviors once more, possibly opening up a new realm beyond. What could it mean to cross an inner horizon? Some solutions of Einstein's equations hint at exotic possibilities. Beyond that inner boundary, the geometry might open into an entirely new region of the universe, perhaps even a pathway to another universe altogether. In these pristine equations, the inner horizon could act like a portal. If we were to somehow move beyond it, we might find ourselves no longer being pulled further inward for a moment, but gliding into a different space that lies hidden behind the singular core. It sounds like science fiction, a secret door in the heart of a black hole, and indeed it stretches credulity. The catch is that this scenario assumes a perfect, undisturbed black hole and a perfectly aimed trajectory. Any deviation, any imperfection at all, and the ring's incredible gravity would catch you. Stray even slightly off the precise center, and you would smash into the ring singularity, where gravity is infinitely strong. That would be just as fatal as hitting a point singularity. The ring may offer a narrow escape route in principle, but in practice, it is like a razor's edge, nearly impossible to balance on. But nature, as we suspect, may not allow such an easy escape from doom. The calm, orderly passage through an inner horizon might be an illusion that exists only in ideal mathematics. In reality, a black hole is rarely an undisturbed, perfectly symmetric object. It formed from collapsing stars and continues to pull in dust, gas, and light. All those disturbances, however tiny, might become magnified monstrously in these depths. The closer we draw to where the inner horizon should be, the more we must wonder, is something brewing here that the equations of a perfect vacuum did not account for? Our journey so far has been eerily smooth and silent, but now an uneasy tension fills the air. It is as if we've entered the eye of a cosmic storm, deceptively peaceful, while unimaginable forces gather around us. Physicists predict that any stray beam of light or flash of radiation that fell in behind us could be catching up now, compressed and blue-shifted into a raging torrent of energy. This theoretical phenomenon is known as mass inflation. The inner horizon becomes a dumping ground for energy, amplifying it to fantastic levels. In effect, the inner horizon might turn into a seething wall of deadly radiation. Were we in a physical craft, this would be the ultimate hazard. A true traveller would be blasted and torn apart by such an onslaught. In this thought journey, however, we have the luxury of pressing on, observing even the unimaginable. The turbulence here is a reminder that the beautiful predictions of a rotating black hole's interior come with a caveat. They might be inherently unstable. It is as if the universe refuses to allow a simple passage through the core. The inner horizon, instead of a doorway, could be a final barricade, chaotic and fiercely defended by the laws of physics. We drift onward, keeping our course toward the heart, while acknowledging the storm that may surround us. The frame dragging has wound space-time tight around us, and we ride its spiral deeper. If there is indeed a wall of energy at the inner horizon, we must cross it in our mind's eye. As we do, we imagine emerging into whatever lies beyond. Perhaps Just for the sake of exploration, we assume an almost perfectly quiet black hole that lets us slip through, so that we can see the mysteries ahead. In the silence after the storm, we continue inward, bracing for what the core itself will reveal. Yet even as we venture further, a part of us knows this tranquility cannot last forever. The rotating interior has given us a glimpse of its fury and its complexity. It reminds us that we are dealing with extremes of nature where our intuitions falter. Ahead, the singularity awaits, the very center of this gravitational trap. But unlike the simple point we might have imagined in a non-rotating hole, this singularity is something different, shaped by the rotation into an odd form. As we leave the inner horizon region behind, we prepare to confront the ultimate mystery at the black hole's core, uncertain and curious about what form it will take. In the deepest darkness at the black hole's core, we finally confront what we have been drawn toward all along. Here lies the singularity, the ultimate collapse of matter and space. Yet what we find is not what one might expect from the simple idea of a single central point. Because this black hole spins, its singularity has been stretched and spun out into a different shape. Instead of an infinitesimal point, the central singularity is like a tiny ring, a loop of infinitely dense mass hanging in the heart of the black hole. If our black hole had no rotation, all the mass would crunch into a point at the very center, a point singularity, an infinitely small location of immeasurable density, marking the end of space-time's road. But rotation changes this finale. The immense angular momentum twists the collapse. Rather than collapsing straight to a point, the mass flings outward in its own rotation, much like a spinning ice skater's arms stretching out. The result predicted by Einstein's theory is this ring singularity, a closed circle of extreme density lying in the black hole's equatorial plane. In a sense, the core has a hole through its middle, a tiny opening encircled by the loop of the singularity. What does it mean for the singularity to be a ring? It is a mind-bending idea. A ring singularity might have an inside and an outside, even if both regions are unfathomably extreme. Imagine a hoop or a donut shape, but made of something not really material at all. It's a place where space and time themselves have collapsed into the bizarre. Through the center of this ring, surprisingly, there is a path that does not run smack into infinite density. It's as if the universe has left a small loophole in the very middle of the maelstrom. If one were perfectly aligned and incredibly lucky, one might pass straight through that central gap. It would be slipping through the eye of the cosmic needle. This possibility is one of the most astonishing outcomes of the math. If you could navigate precisely through the ring singularity's center, you might avoid being torn apart by hitting the singularity itself. Instead of colliding with an all-destroying point, you'd thread through a narrow tunnel of sorts. And where would you emerge if that happened? The equations hint at something astonishing. You could find yourself flung out into another patch of space-time entirely, perhaps into a different universe, or a distant part of our own universe in another era. The ring singularity, in theory, could act like a bridge or a door to an elsewhere. It sounds like pure fantasy, a natural wormhole created by a rotating black hole. And indeed, it stretches credulity and known physics. The catch, as mentioned, is that this scenario assumes a perfectly smooth, unperturbed black hole and an almost impossibly precise trajectory. Any stray perturbation or slight misalignment, and the ring's staggering gravitational forces would snare you. If you approach off-center by even the tiniest margin, you would collide with the ring singularity itself, where tidal forces are infinitely strong. That encounter would be instantly fatal and final. In practice, no spacecraft or traveler could hope to find that needle's eye path through the ring. The ring singularity may offer a theoretical escape route, but it's one that nature almost certainly slams shut with even the smallest disturbance. Contrast this with the simpler point singularity of a non-rotating black hole. There, no such escape route exists at all. No matter how you approach, you inevitably meet the singularity head-on. In a Schwarzschild black hole, one without spin, the singularity sits at the absolute center, and every direction inward leads directly to it. It is a true dead end in space-time. The ring singularity is, oddly enough, not a dead end in the mathematics. It's more like a fork in the road where the usual laws break down, offering multiple pathways that should never exist in our ordinary universe. However, even if a ring singularity mathematically provides another path, it comes with other bizarre consequences. Close to that ring, space and time get mixed up in extraordinary ways. Theoretical physicists have found that near a ring singularity, it may be possible to find paths that loop back on themselves in time. These are called closed time-like curves, essentially gravity's version of a time machine. If you were near the ring singularity and somehow able to survive the forces, you might, in theory, travel in a certain loop and end up back at an earlier moment of your own journey. It's an unsettling sign of how utterly the normal order of cause and effect can break down in such extreme conditions. Such strange possibilities make it clear that the term singularity is not a one-size-fits-all phenomenon. Whether point or ring-shaped, it represents a realm where the rules we know cease to function in any familiar way. The ring singularity, while different in shape, is just as confounding as the point singularity. Both indicate a breakdown of space and time as we understand them. The differences teach us that what lies at a black hole's core isn't uniform. It depends on the cosmic history of the black hole, on its spin, and perhaps other factors like electric charge. In our current journey, we face the ring singularity of a rotating black hole. We cannot see it with our eyes. It emits no light, and any light shining upon it would simply vanish from view. But we sense its presence in the dramatic intensification of gravitational forces all around us. Space is curving more steeply here than anywhere else in the universe. The ring itself might cast a sort of shadow against any background glow, warping light around it into strange arcs. If we had a way to illuminate the scene, perhaps we'd see an eerie halo or distortions marking where the ring lies, rather than the ring itself. It is the very definition of an event horizon's promise. No information from within can get out, and that includes any direct signal of what the singularity looks like. The only light here is our understanding, scant as it is. We hover conceptually near this final veil. The point versus ring difference gives a glimpse of how varied black holes can be in their extreme interiors. It humbles us, reminding us that these aren't simple monolithic objects, but complex outcomes of gravity and cosmic motion. As we contemplate this ring of doom and the hypothetical hole through its center, we also recognize how fragile these ideas are. A slight perturbation in reality would close that hole and reduce the ring to the same absolute trap as any point singularity. Reality, it seems, does not easily allow escapes from its gravest prisons. Lingering near this unseen ring, we are filled with a mix of awe and trepidation. This is the beating heart of the black hole, different in shape but equal in mystery to any singularity. It is the culmination of our journey inward so far. And now, aware of its nature, we turn our thoughts to the journey's final leg. We have not yet reached the singularity itself, but we are ever so close. The forces of the black hole's core are rising around us, ready to unleash their full power. We brace ourselves for the last plunge toward this ring of darkness, knowing that beyond a certain point, even the best theories we have will begin to falter. Poised on the edge of the unknown, we take a moment to consider an intriguing fact. Not everything our equations call a singularity is truly a physical curtain call for reality. Sometimes, the appearance of a singularity is a trick of our perspective, a flaw in the coordinates or the language we're using to describe spacetime. It wouldn't be the first time that nature proved smoother than our mathematical picture of it. It reminds us that sometimes what appears to be the edge of reality might simply be the edge of our understanding. Recall the event horizon we crossed earlier. In the early days of black hole theory, that very horizon was mistaken for a singularity. The original mathematical description of a black hole, formulated by Carl Schwarzschild in 1916, made it seem as if something catastrophic happened at the Schwarzschild radius, the event horizon. The equations blew up there. Time appeared to stand still, and space seemed to end. To many, it looked like a genuine singularity, a boundary beyond which nothing could exist. And yet, we experienced firsthand that falling through the horizon was uneventful. There was no physical barrier, no wall of infinite gravity at that radius. The apparent blow-up was a quirk of Schwarzschild's coordinates, not a feature of the world itself. It took decades for physicists to fully understand this. New coordinate systems were devised. Names like Eddington-Finkelstein and Kruskal-Sekares became important in the 1950s and 60s, which allowed one to describe spacetime in a way that smoothly extends across the event horizon. In these better-suited coordinates, nothing particularly special happens at the horizon. It's revealed as what it truly is, a point of no return. Yes, but not a point of infinite density or energy. In other words, the horizon is a property of how information and causality are structured around the black hole, not a material surface. The singularity that Schwarzschild's original math seemed to show at the horizon was an illusion, born from an awkward choice of perspective. This lesson is profound. It tells us that when our calculations yield infinities, we must ask, is nature really infinite here? Or have we just chosen a poor vantage point? Imagine looking at the Earth on a flat map. The North Pole might appear stretched into a weird line across the top of the map, or all the lines of longitude might converge into a jumbled point. To someone unfamiliar with globes, it might seem like the Earth has a bizarre edge or tear at the pole. But of course, in reality, the Earth is smooth at the poles. It's the map projection that failed to represent that smoothly. Similarly, the event horizon was like the North Pole of our spacetime coordinate map, a place where the coordinate grid broke down, even though spacetime itself was just fine, albeit extremely curved. Inside a rotating black hole, we have even more complicated coordinate issues. We encountered the idea of an inner horizon, another place where naive calculations might blow up. In an idealized, perfectly symmetric rotating black hole described by the Kerr solution, one can mathematically navigate beyond that inner horizon to find an extension of space-time. The coordinates we started with aren't enough to chart that journey, but with a clever change, a kind of mathematical compass reset, the path can be continued in theory. What seemed like a dead end in one description becomes a door in another. Yet, whether that door is real or slammed shut by physical reality via chaos and radiation is still up for debate. The distinction between a true physical singularity and a mere coordinate singularity is crucial. A true singularity is something no trick of math can eliminate. It's where quantities like density or space-time curvature genuinely become infinite, signaling the breakdown of the laws of physics as we know them. The central point, or ring, we are now approaching appears to be one of these genuine singularities in classical general relativity. No matter what coordinate system you use, if you examine invariants, the things in the equations that have physical meaning independent of coordinates, they blow up to infinity at that core. That is a strong indication we are dealing with a real physical problem, not just a misdescription. Even so, some physicists argue that what we call a singularity might still be a hint that our theories are incomplete, rather than an actual physical end. Just as new coordinates removed the illusion of a singularity at the horizon, perhaps a new kind of physics, likely a quantum theory of gravity, will one day remove the infinity at the core and show us something finite and comprehensible in its place. In other words, the singularity we anticipate ahead could be the result of using general relativity in a realm where it no longer applies. It might not be a true end of spacetime in a more fundamental, yet to be discovered description of nature. Until that new description comes, though, the singularity remains a looming puzzle, a place where our best understanding falls apart. Throughout our journey, we've learned that context and perspective matter. What appears impossible or undefined in one frame of reference can be perfectly routine in another. Crossing the event horizon felt normal to us because our frame of reference was falling along with space. To someone far away trying to use their frame to make sense of it, it looked like time froze at the horizon. Both perspectives were using their own coordinates to describe the event, and one of them was misled by that choice. Here, inside the black hole, we must be careful not to take every divergence in our equations at face value. We ask, is this the end of space-time, or just the end of our chart? So far, every truly dangerous singularity we know of, the kind that destroys the rules of physics, has been safely tucked away behind an event horizon. The horizon itself, once properly understood, is just a doorway, not a hazard. And beyond it, hidden from the outside universe, lurks the genuine singularity where our models blow up. This separation is oddly comforting. It means that from the outside, the chaos at a black hole's core cannot influence the universe beyond, at least not in any direct, observable manner. A distant observer never sees the singularity naked. They see only the event horizon guarding it. Some scientists suspect this is not a coincidence, but a fundamental principle of our universe. Nature may censor singularities from our view, always wrapping them in horizons. This idea is known as the cosmic censorship conjecture, a kind of promise that we will never see a raw singularity exposed without a horizon to hide it. Roger Penrose proposed it in the late 1960s, whimsically dubbing nature a cosmic censor that forbids the scandal of a naked singularity. As we stand on the brink of encountering the singularity ourselves, from the inside, where it's effectively laid bare to us, this notion of cosmic censorship becomes ever more intriguing. Is it an absolute law of nature, or are there loopholes? Our reflections turn to that debate, as we wonder what would happen if a singularity were left unclothed for all the universe to see. The notion that nature might always hide singularities behind horizons is cosmic censorship. It's a conjecture, not a proven law, but so far it has stood strong. In simple terms, it says nature abhors a naked singularity. Any time a singularity is about to form from collapse, the conjecture claims that a shroud, an event horizon, will form around it, preventing the outside universe from directly witnessing the singularity's havoc. We have seen this with black holes. A star collapses, a horizon appears, and whatever singularity exists at the center is safely sealed inside. But is this always the case? What if, Under some extreme circumstance, a singularity could form without a horizon. Such a phenomenon would be a naked singularity, an exposed edge of spacetime where density becomes infinite and the usual rules break down. It would lay bare the most extreme secrets of gravity with no veil to hide them. Why would a naked singularity be so troubling? Because it would represent a place where physics, as we know it, breaks down. Yet its effects could, in principle, escape and influence the rest of the universe. Inside a black hole, the breakdown at the singularity doesn't bother us directly. It's quarantined. But a naked singularity could spew out its chaos for all to see. The usual rules, cause and effect, predictability of outcomes, might crumble in its vicinity. It could be like having a tiny piece of the Big Bang's chaos appear in the present universe, with no protective shell around it. That prospect is both tantalizing and alarming, and most physicists believe nature is kind enough to prevent it. Let's consider how a naked singularity might arise, theoretically. One scenario involves pushing a black hole beyond its limits. Black holes have two key extremes: spin and charge. For a rotating black hole, Kerr black hole, there is a maximum rate of spin relative to its mass. If it spins too fast, beyond what's called the extremal limit, the formulas suggest the horizons would disappear, leaving the singularity naked. Likewise, for a charged black hole, Reissner-Nordström black hole, if the electric charge is too high relative to its mass, the horizon would vanish and the singularity would be exposed. These thresholds mark the boundary between a black hole and a hypothetical naked singularity. So, what if we tried to create such a situation? Imagine feeding a black hole more and more angular momentum, trying to spin it up faster than nature's supposed limit. With each addition, the black hole's event horizon would stretch and deform. But something interesting happens. The black hole also gains mass with each new piece of matter, keeping the spin-to-mass ratio in check. Many physicists have analysed these thought experiments and found that some mechanism always swoops in to prevent overspinning. For instance, just as the black hole nears the dangerous fast spin limit, additional incoming matter might be flung away by gravitational slingshot effects. It can also release energy, like gravitational waves, instead of driving the spin further. It's as if the black hole has a built-in regulator. Try to spin it too fast, and it refuses by shedding excess energy or mass. The same goes for charging a black hole beyond its limit. If we pour charge into a black hole, say by throwing in a multitude of charged particles, the black hole's electric field grows. Eventually, that field becomes so strong that it repels further like charges and even pulls in opposite charges from the surrounding environment to neutralize itself. The vacuum around the black hole might spontaneously spawn particle-antiparticle pairs when fields are extreme, effectively discharging the hole by feeding it opposite charges. All these processes conspire to stop us from ever accumulating so much charge that the horizon disappears. These aren't rigorous proofs, but they are reassuring hints. The cosmic censorship conjecture remains just that, a conjecture. No one has proven it in general, and over the years scientists have devised clever, and sometimes highly contrived, ways to challenge it. Some computer simulations of hypothetical gravitational collapses have suggested that, under very special symmetrical conditions, a naked singularity might form. For example, if a perfectly smooth sphere of matter imploded instantaneously, or if an infinitely long, thin spindle of matter collapsed, the math can produce a naked singularity solution. However, the slightest imperfection in those setups typically restores the horizon or avoids the singularity altogether. It's like trying to balance a pencil on its tip, theoretically possible in a perfect scenario, but any real-world disturbance makes it fall. However, even these studies are illuminating. They show us how delicately nature seems to avoid exposing singularities. One famous potential example of a naked singularity in theory is the so-called instantaneous implosion model, where gravity compresses a region of space-time so quickly that a horizon doesn't have time to form. Another involves colliding waves or beams of extreme energy. Calculations show that under nearly unimaginable conditions, two ultra-powerful shock fronts converging could compress space-time so intensely at the collision point that a singularity forms in the open, without a horizon to hide it. This scenario, too, demands perfect symmetry and tremendous concentration of energy. The slightest asymmetry, or anything less than an idealized infinite energy, and the outcome would be a strong yet ordinary gravitational field, not an exposed singularity. These thought experiments push the limits of cosmic censorship, probing whether nature might allow such cosmic oddities, even for a fleeting moment. Astrophysical observations also give weight to cosmic censorship. When we observe black holes in the universe, whether through X-ray emissions from accretion disks or through gravitational waves from mergers, we consistently find objects that behave as if horizons are present. Take the gravitational wave signals detected by the LIGO observatory from merging black holes. They match the patterns expected when horizons are ringing and settling down after a merger. If naked singularities were popping up, we might see telltale bursts or deviations in those signals. But we have not. In fact, when scientists detected those waves from black holes crashing together, they found nothing anomalous, just two black holes merging into a bigger one with an intact horizon. Even in the throes of such cosmic violence, no mysterious signal hinted at a horizonless object. So far, every time we look closely, either the scenarios that produce naked singularities require unrealistic conditions, or quantum effects are expected to intervene just in time. What if cosmic censorship were violated, though? Physicists speculate on some wild consequences. A naked singularity might act like a cosmic flashbulb, emitting a burst of high-energy radiation as it forms, since nothing would trap the extreme energy densities. For instance, some have imagined that a naked singularity could spew out flashes of energy or matter without warning, bursts of radiation appearing from a point in space where nothing should be. It would be as if effect could precede cause, a breakdown of the normal order. Without a horizon to hide its influence, a naked singularity might also allow gravity to form time loops that extend into the wider universe, raising the bizarre possibility of causality violations that outside observers could in principle see. In short, it could open Pandora's box. Unpredictable signals, or even the means to travel backward in time, might emerge. These prospects threaten the logical order of our universe, which is why many suspect nature has built-in safeguards. The debate over cosmic censorship is not just academic. It strikes at the heart of whether our physical theories can be complete. If cosmic censorship holds true, it's a comforting sign that general relativity, even with its singularities, maintains a kind of consistency. It hides its own failures behind horizons. If it fails, then classical general relativity on its own could produce unpredictable, observable effects, strongly signaling the need for new physics, like quantum gravity, to take over in those situations. Many suspect that even if classical relativity might allow a naked singularity in principle, quantum effects would swoop in to save the day, preventing the singularity from fully exposing itself or muting its influence. As of today, cosmic censorship remains unproven. Penrose's conjecture stands as a guiding principle, challenging researchers to either prove it or find a genuine counterexample. It's like a dare to the universe. Show us if you can break this rule. So far, the universe has been a cooperative partner to the conjecture, at least in every natural phenomenon we've observed or realistically modelled. But the conversation isn't over. Theoretical physicists continue to probe the edges of relativity for signs of censorship breaking down, because in those cracks might lie new physics or deeper truths about space-time. Here, at our vantage, deep inside a black hole, the idea of cosmic censorship gains a personal dimension. We are about to encounter a singularity face to face, essentially experiencing a naked singularity from our own infalling perspective, though to the outside world we remain hidden behind the horizon. For us, the singularity will not be censored at all. We will confront it directly. In doing so, we step into a realm where classical physics gives no guidance. Whether or not cosmic censorship holds in the external universe, for us in here, the censorship is about to end. We must rely on something beyond classical equations to imagine what comes next. This realization sets the stage for our final approach, the last microseconds as we near the Planck scale mysteries where classical physics must let go. This is the end game of our journey, the final fraction of a second, shrinking down to unthinkably brief moments as we approach the very core. In truth, calling it a fraction of a second doesn't capture the extremity of it. It is better described in the language of Planck time, the smallest unit of time with any physical meaning, about 10 to the power of minus 43 seconds. That is a 10 millionth of a trillionth of a trillionth of a trillionth of a second. In these last instants, as our fall continues, time itself is about to cease having meaning. Distances have contracted to the Planck length scale, around 10 to the minus 35 meters, far smaller than a single atom's nucleus, smaller even than a proton by unimaginable orders of magnitude. We are now plunging through scales where the very fabric of space-time becomes grainy and unpredictable. Reality as we know it is disintegrating into something fundamentally unknowable. Up to this point, we have trusted general relativity to guide us. Its equations have described space-time as a smooth continuum, bending and curving under mass and energy. But general relativity was never intended for realms this extreme. As we reach the Planck scale, the smooth sheet of space-time envisioned by Einstein likely frays into something else, perhaps a quantum foam of flickering, probabilistic space-time quanta. The tidal forces, curvature, and energy densities in our vicinity are reaching values so high that they defy classical description. According to general relativity's equations, we are on a collision course with an infinitesimal point of infinite density, the singularity, in literally no time at all. But infinities and zero sizes are nature's way of telling us our theory has run out of road. General relativity simply cannot be trusted in this realm. In other words, we now require new physics to continue the story beyond this point. In these last microseconds, if we had any instruments left, they would be registering nonsense. Any clock we carry would either be destroyed or reading something meaningless as time and space lose their ordinary definitions. We, as coherent observers made of organized matter, are no more. By now, we have been reduced to a rushing stream of fundamental particles and energy quanta. Those quanta themselves are in turmoil. Gravity's pull is now comparable to the forces binding those particles together. The familiar distinctions between forces, gravity, electromagnetism, nuclear forces, begin to blur when energies are this extreme. We are in a regime where the next step requires a theory that unifies these forces, a theory humans have pursued but not yet fully found, a quantum theory of gravity. For decades, physicists have struggled to merge quantum mechanics with gravity to explain conditions exactly like these. Without such a theory, our understanding halts at this threshold. It is often called the Holy Grail of modern physics. Quantum gravity is the missing piece of the puzzle that would tell us what happens right here, at the precipice of a black hole's singularity. In this realm, space and time might no longer be continuous. They could come in discrete chunks, like grains of sand that make up a beach, but far smaller, the grains of spacetime at the Planck scale. If that is true, then the concept of an infinitely small point might be replaced by something else entirely. Perhaps the singularity is not a point at all, but rather a tiny region where space and time themselves have been quantized into something novel. Our classical description breaks down, not because physics ends, but because we need a different vocabulary and set of laws to describe what's happening. One leading idea is that of a quantum bounce. Instead of matter collapsing to an infinitely dense point, quantum effects might halt the collapse at an incredibly high but finite density. At that moment, like a compressed spring releasing, the core could rebound. This concept essentially replaces a singular ending with the possibility of a new beginning. Some theorists envision the heart of a black hole rebounding outward in a new form, essentially transforming into a white hole that spews out what fell in, but perhaps far in the future, or even in another universe. This bounce might be almost instantaneous from our perspective inside, yet due to extreme time dilation, it could correspond to an eons-long process to an outside observer. In such scenarios, the singularity, as predicted by relativity, never quite forms. It's averted by a sort of quantum pushback, and the energy and information swallowed by the black hole erupt out in some altered form elsewhere or elsewhen. Effectively, the black hole would eventually vent out its contents instead of holding them forever. Another intriguing possibility is that the black hole's core becomes a gateway to a new universe. Some interpretations of the mathematics, particularly for a rotating black hole in the idealized case, hint that the interior could connect through the singularity to an entirely new, expanding domain of spacetime. Imagine, the singularity we are falling into might, beyond the veil of quantum gravity, be akin to a big bang for a baby universe on the other side. In that picture, our journey doesn't terminate. It simply carries us into a new continuum that buds off from our parent universe. We would never be able to report back to our original universe, of course. That bridge is strictly one way and utterly destructive to anything that attempts to cross. For an outside observer, such an internal big bang would remain forever hidden behind the black hole's horizon. Whether nature truly allows a black hole to spawn a new universe remains an open question. As fantastical as it sounds, this scenario arises from serious solutions to Einstein's equations, though whether quantum reality would permit such a continuation is deeply uncertain. On the other hand, some proposals suggest that nothing so dramatic as a new universe occurs. Instead, the black hole might reach a final equilibrium state at the Planck scale. In these models, the collapse grinds to a halt when quantum degeneracy pressure or other effects counteract gravity's squeeze. The result could be a sort of frozen relic, a Planck-sized nugget of unbelievably dense stuff, a remnant that eventually also fades, or perhaps remains eternally as a stable, dark memory of what once was. Meanwhile, proponents of string theory envision something different, that a black hole might not have any singular point at all, but rather that its mass is spread out in a tight ball of tangled strings and quantum fields, sometimes dubbed a fuzzball. In that picture, the interior never crunches to a point. It's all dissolved into a seething quantum mass, effectively removing the singularity entirely. From the outside, the black hole might then slowly evaporate via Hawking radiation. the trickle of particles that quantum physics predicts black holes emit, leaving behind perhaps a small remnant that eventually also fades or remains as a stable, dark memory of what once was. In effect, the universe would never witness any grand explosion. The black hole would simply fade away, leaving behind only this tiny residue of its existence. Either way, no violent outburst marks the black hole's final fate. Each of these ideas, a quantum bounce to a white hole, a baby universe beyond the singularity, a stable Planck scale remnant, or even a string theory fuzzball, is speculative. We simply do not yet know which, if any, is correct. What they all have in common is that they avoid the meaningless infinities of a classical singularity. They suggest that there is something beyond that infinite wall, that nature finds a way to resolve the paradox. Maybe the singularity is not an abrupt end to everything, but rather a portal or a transformation. Perhaps the information that seemed lost is conserved after all, encoded in whatever new form emerges from the collapse. This ties into the famed black hole information paradox, the puzzle of whether information is truly lost in a black hole. Each of these quantum possibilities provides a potential escape route for information, ensuring that the fundamental laws of physics aren't broken, even when a black hole dies. For us, however, as travelers plunging in, none of these conjectures changes the immediate reality that we cannot survive this passage in any recognizable form. We have reached the limit of what we as physical beings can experience. Our story as observers effectively stops here, at the cusp of the unknown. If there is an after, whether it be another universe, an explosion into a white hole, or a strange quantum object left behind, we would not live to see it in our current form. In these vanishing instants of proper time left to us, we have essentially become one with the black hole's singular fate. And yet, we experience these last moments in a kind of calm resignation. By now, pain is beyond perception. Our nerves would have disintegrated or gone numb as our form unraveled. Even fear has little meaning at this extreme. There is only acceptance of the inevitable, a quietude as the final step draws near. Our individual journey meets its end, but the quest to understand what truly happens here is far from over. We hand off the baton from the realm of experience to the realm of theory and imagination. The questions raised by this plunge, about the ultimate unity of nature's laws, about how information and cause and effect operate at the edge of time and space, remain to be answered by future science. We are reminded that every end in science is also a beginning. The end of known physics is the beginning of a new frontier of discovery. As our final moment arrives, we find a strange calm in knowing we have traced out every step that known physics allows. We have voyaged from the serene vastness of space to the violent grip of a black hole, right up to the edge of reality as we understand it. Now, as the singularity, or whatever reality replaces it, greets us, we have no more guideposts. This is where our narrated journey must yield to silence and uncertainty. We have, in a sense, reached the center of the black hole. But it is a center, not of answers, but of questions. The singularity challenges not only our physics, but also our imagination. It marks a boundary where meaning itself begins to blur, where space and time defy our conventional understanding. Confronted with this edge of reality, we are reminded of both our limitations and our relentless curiosity. Black holes were once purely theoretical, yet we have now photographed the shadow of one, listened to the tremors of their collisions, and built equations to describe their extremes. Perhaps one day, the singularity too will evolve from a mathematical enigma to an empirically understood phenomenon. Until that day, it remains a potent symbol of the unknown, a dark, hidden beacon that compels us to keep questioning and keep exploring. And so, as this part of our journey draws to a close, we have reached the very frontier of current understanding. The next steps lie in the realm of bold speculation and future discovery. In the following part of this odyssey, we will dare to imagine crossing that frontier, peering through the veil that nature has drawn over the singularity and seeing what might lie beyond. In the silent depths of space, two black holes drift in a tightening orbit. They circle one another in a gravitational dance that quickens over millennia, slowly at first, then faster with each passing eon. Their spirals contract. As they draw closer, these heavy dark bodies whip around at incredible speeds, sending subtle shivers through the fabric of spacetime itself. Though no light escapes their event horizons, the very structure of space ripples outward from the merging pair. These ripples are gravitational waves, spreading in all directions, like the concentric circles formed when a stone is dropped into a still pond. Across unimaginable distances, the waves carry the story of the black hole's final moments. Each wave is a whisper in space-time, an echo of titanic masses in motion. In their last seconds, the two black holes move at nearly half the speed of light. They circle each other dozens of times per second, warping space and time to extremes. The rhythm of their orbit speeds up into a frenzied crescendo. Finally, the black holes collide and coalesce into one larger black hole. In that violent embrace, a portion of their mass is transformed into a surge of gravitational energy. A powerful ripple flings outwards, as if the universe itself rings like a great cosmic bell. That wavefront travels through the cosmos, weakening as it expands, but never faltering in its steady journey. After billions of years and countless light years, the faint signal washes through our solar system. On Earth, on a quiet day, an exquisitely sensitive observatory subtly trembles. Deep within its long vacuum tunnels, laser beams shift by a distance smaller than an atom's nucleus. The instruments have detected the passing gravitational wave, a tiny distortion in space stretching one dimension while squeezing another, then reversing. This moment marked a new age of astronomy. For the first time, humanity had heard the merger of black holes. The faint chirp recorded in the detector was the dying song of two black holes becoming one. Encoded in that brief rising tone was a wealth of information. It told of the masses of the black holes, their distance, and the energy unleashed as they merged. This was a direct confirmation that black holes not only exist, but they collide and merge in the dark cosmos. Listening to gravitational waves is unlike seeing light or X-rays. It is more like feeling the tremor of a distant explosion echoing through solid ground. These waves carry information that no light could bring us, because black hole mergers produce hardly any electromagnetic glow. The waves are messengers of gravity alone. Through them, astronomers learned that pairs of black holes roam the universe and occasionally meet in fatal encounters. After the merger, the newly formed black hole itself vibrates briefly, like a struck drum. This is the ring-down phase. The shape of space around the new black hole quivers as the object settles into a stable form. These final vibrations also travel outward as gravitational waves. By analyzing those, scientists confirmed that the end product behaves exactly as general relativity predicts: a larger black hole with a smooth, featureless outer boundary. In other words, the waves verified that black holes ring in the way Einstein's equations said they would, offering yet more evidence of their true nature. Even before they collide, the spiraling black holes broadcast their approach through gravitational waves that steadily increase in frequency and strength. It is akin to a rising musical note in the silence of space, a telltale chirp that grows higher and louder as the black holes whirl faster and closer. In the final instance, their speed and gravitational fury peak. For a brief fraction of a second, the power they radiate in these waves exceeds the light from all stars in the observable universe combined. Then, abruptly, the note stops. The two have become one, and what follows is the gentle fading hum of the ringdown. Crucially, these cosmic vibrations travel at the speed of light, passing through galaxies, dust, and planets without effort. Unlike light, they are not absorbed or scattered. They carry a pristine record of the event. By the time the wave reaches Earth, it is incredibly faint, causing relative movements in the detector's arms on the order of 1 part in 1,000 trillion. This tiny motion, smaller than the width of a proton, is what our exquisite instruments are built to sense. To achieve this, engineers isolated the detectors from ordinary noise, seismic tremors, traffic, even distant ocean waves. Only with such care can the subtle stretching of space-time be teased out from the background. The success of these observatories was far from guaranteed. The concept of hearing black holes through gravitational waves had been discussed for decades, but it was hard to believe it would truly work. When the first signal arrived, it took months of analysis to convince scientists that it was real and not an artifact or mistake. But it was real. The waveform's shape matched precisely what theory predicted for two heavy black holes merging. It was as though we had a specific melody in mind, and the universe played it back on cue. The confidence grew as additional detectors in Europe and elsewhere also picked up the signature, allowing astronomers to verify its origin and roughly pinpoint the patch of sky it came from. Each new detection since that first breakthrough has enriched our understanding. We have catalogued collisions between black holes of different sizes and spins, some in remote young galaxies, others perhaps in dense stellar nurseries, where multiple black holes form and interact. In one case, astronomers heard an especially clear and loud chirp from a merger that produced a black hole of about 150 solar masses, evidence of a long-sought intermediate mass range bridging the gap between small stellar remnants and supermassive black holes. In other instances, the data hinted at black holes with slight tilts or spins misaligned with their orbit, raising questions about how these binaries form. Piece by piece, the gravitational wave sky is revealing an invisible population of black holes and providing clues to their origins. Gravitational wave observatories on Earth, with names like LIGO and Virgo, act as cosmic ears pressed to the fabric of space-time. They are deaf to light, but acutely sensitive to the slightest tremble of space itself. With each detection, astronomers refine their understanding of how often black holes merge and how big they can grow. In one extraordinary event, two hefty black holes combined into an even more massive one, in a system that challenged prior assumptions about how such heavy black holes form. These gravitational echoes are fleeting, lasting barely a second or two in our detectors, but their implications are profound. They allow us to confirm fundamental laws of physics under conditions that no laboratory on Earth can replicate. When two black holes merged and were heard across the cosmos, one of Stephen Hawking's famous predictions was confirmed. The horizon area of the final black hole was larger than the sum of its parts, as no information is lost and the total entropy increases. Even in the stillness of a vacuum, the language of gravity carries clear meaning. Now we know that space itself can serve as a record of cataclysmic black hole events. It remembers in the form of gravitational waves that ripple outward endlessly. By catching these whispers, we effectively read a cosmic log of black hole interactions. In our journey to understand black holes, this ability to listen has been revolutionary. It has shown us merging black holes in complete darkness, proving that even the most invisible collisions can be observed. Yet gravitational waves are just one way we have learned to perceive the unseeable. Black holes also leave shadows and reflections in light itself. Through different kinds of cosmic messengers, from high-energy photons to subtle stellar motions, we have found many ways to sense a black hole's presence. Our voyage continues as we explore how black holes reveal themselves through the light and motion around them. Just as sound can reveal the unseen, so too can light in its many forms. Black holes themselves emit no light, but they rarely exist in isolation. Often they are accompanied by gas, dust, or even whole stars that they grip with their formidable gravity. As this matter falls inwards, it heats up and shines, creating a beacon that marks the black hole's presence. In fact, long before we could detect gravitational waves, astronomers found black holes by noticing unusual sources of high-energy light in the sky. In one common scenario, a black hole orbits quietly with a normal star as a pair. To the eye, the star might appear ordinary, but something strange is afoot. The star wobbles and its light shifts, revealing it is tugged by a massive, unseen companion. Furthermore, space telescopes detect intense X-ray radiation coming from the system, far more energetic than any normal star could produce. What could shine so brightly in X-rays, yet remain invisible in ordinary light? The answer: a black hole feeding on its companion's gas. As the black hole's gravity draws matter off the outer layers of the star, the gas forms a swirling disk around the black hole, compressing and heating to millions of degrees. At such temperatures, it emits X-rays. The result is an X-ray binary, a pair of objects, one a star, the other a black hole, locked in an intimate and ultimately fatal relationship of matter transfer. These X-ray binaries flicker and hum with changing light as the black hole's meal is not steady. Sometimes the flow of gas is sporadic, causing sudden outbursts. Astronomers watch as an otherwise faint source in the sky brightens dramatically in X-rays or gamma rays and then settles down again. Each flare is a surge of energy released by a fresh gulp of material by the black hole. Over time, careful observations of the companion star's orbit tell us the mass of the unseen object. If it exceeds a few times the mass of our Sun and has no light of its own, nothing but a black hole fits the description. Thus, by the 1970s, the first strong evidence for a stellar mass black hole emerged from an object named Cygnus X1, an X-ray source in the constellation Cygnus. It was an unseen gravitational force pulling matter off a blue supergiant star, shining brightly in X-rays as the matter fell into darkness. While stellar black holes announce themselves in these violent X-ray courtships, far more massive black holes reside in galaxy cores and can create even more extraordinary beacons. In the heart of distant galaxies, astronomers discovered tiny, brilliant sources that outshone all the stars of their host galaxies combined. At first, these points of light looked almost like stars, hence their name, quasi-stellar objects, or quasars. But their light bore fingerprints of unimaginable distances, meaning they shone from the early eras of the universe, billions of light years away. To be visible from so far, their power output had to be staggering. We now understand that a quasar is the blazing core of a young galaxy, illuminated by a supermassive black hole devouring matter at a furious rate. Gas and dust spiral into the giant black hole's gravitational grip, forming an accretion disk much larger than those of X-ray binaries. But the physics is similar, only scaled up. Near the center, temperatures soar to hundreds of thousands or millions of degrees, and the disk radiates across the spectrum. Visible light, ultraviolet, X-rays. A quasar's disk and its energetic subatomic particle jets can pump out more light than entire galaxies, turning the black hole into a cosmic lighthouse that can be seen across the universe. The irony is profound. The darkest objects in the cosmos can create the brightest lights when fed with sufficient fuel. Quasars provided the first indirect evidence that supermassive black holes, millions to billions of times the mass of the Sun, were real. Each quasar is like a vivid signpost marking a feeding black hole. By studying the spectra of quasar light, scientists have measured the incredible speeds of gas orbiting these monsters, sometimes a few % of the speed of light. Such extreme velocities in a small region can only be explained by a colossal mass concentrated at the center, again pointing to a black hole. Over decades, thousands of quasars have been catalogued, each one a clue to the growth of black holes and the evolution of galaxies in the young universe. Not all black holes are constantly feasting. Some lie dormant for ages until an unlucky visitor wanders too close. Imagine a star passing near a galaxy's central black hole after orbiting in peace for eons. As it ventures near, the star's far side feels less gravitational pull than the near side, causing a huge difference in forces, a tidal stretching beyond what the star can endure. In a matter of hours, the star is pulled apart in a gravitational tug-of-war. This is a tidal disruption event. The stellar remnants, now a stream of gas, whirl around the black hole. Roughly half of that gas might be flung away into space, but the rest is captured, suddenly dumping onto the black hole's accretion disk. From Earth, astronomers notice something astonishing. A previously quiet galactic nucleus flares up, shining brilliantly in ultraviolet and X-ray light, and sometimes visible light. It's as if a new star has appeared where none was before, then slowly fades over months or years. What they are witnessing is the black hole consuming the remnants of the torn-apart star. The flare's brightness can rival a supernova, the explosion of a star, but with a distinctive behavior and spectral signature that betrays its true identity. As the surge of light gradually diminishes, astronomers gather clues from it: the temperature of the flaring gas, the speed at which it is being swallowed, and even the size of the region emitting the light. Occasionally, a tidal disruption event produces not just a spherical flare, but narrow, high-speed jets of particles that blast outward from the poles of the black hole's spin axis. If we are lucky enough that such a jet points roughly in our direction, the observed light is even more dramatic, boosted by the jet's relativistic speed. A mundane galaxy can suddenly become one of the brightest objects in the sky for a short time. These rare, spectacular episodes reinforce the picture of black holes as cosmic engines, mostly quiet, but capable of sudden ferocious output when fuel becomes available. In some stellar black hole systems, the feast of infalling gas also powers jets of particles that shoot out into space at nearly light speed. These are sometimes called micro-quasars because they behave like miniature versions of the quasars in galaxy cores. The jets, emitting in radio waves, can extend trillions of kilometers from a stellar black hole, creating radio flashes that vary over days or weeks. Such phenomena demonstrate that even a small black hole, given sufficient fuel, can mimic its supermassive cousins on a smaller stage. Quasars themselves often exhibit gigantic jets, spearing out from their nuclei and glowing in radio and X-ray light far beyond the host galaxy's visible boundaries. The central black hole's rotation, coupled with magnetic fields in the accretion disk, is thought to fling these twin beams of plasma outward. Some jets remain tightly focused across hundreds of thousands of light-years, a feat that still astonishes scientists. These jets provide another indirect clue to a black hole's presence and influence, as only a rapidly spinning, accreting black hole could generate such collimated, powerful streams of energy. When we observe distant galaxies with long, lance-like radio jets, we are effectively seeing a black hole's handiwork sculpting the intergalactic medium. Perhaps one of the most important lessons from these luminous signals is that black holes are common and central in the architecture of the cosmos. The detection of quasars implied that supermassive black holes were not exotic anomalies, but likely present in many, if not all, large galaxies, flaring into brilliance only when actively feeding. The discovery of numerous tidal disruption flares in otherwise unremarkable galaxies further cemented this idea. If a dormant galaxy nucleus suddenly erupts in light, we realize a silent black hole was lying in wait there all along. In our own Milky Way, we suspect our central black hole has torn apart stars in the distant past, leaving faint scars of X-ray emissions that hint at ancient feeding episodes. By observing these various forms of light in the darkness, astronomers piece together the life story of black holes, from the steady glimmer of a star's stolen gas in an X-ray binary to the steady blaze of a quasar across billions of light-years, to the sudden flare of a disrupted star. Each phenomenon teaches us how black holes interact with their surroundings. They reveal how black holes grow, how they influence their environment, and how often they stir from slumber to dine. These brilliant lights are proxies for the invisible object at their center, illuminating the darkness indirectly. Still, one might wonder, could we ever witness the immediate vicinity of a black hole, not just its far-reaching effects? For a long time, this remained in the realm of speculation. But with ingenuity and global cooperation, scientists have managed to effectively turn our entire planet into a giant observing dish, capturing an image of a black hole's silhouette and the glowing ring of material on its doorstep. For generations, black holes lived only in theory and imagination. They were depicted in illustrations or described in equations, but no direct sight of one seemed possible. How do you photograph a thing that swallows light itself? The key, it turned out, was not to capture the black hole directly, but its shadow against a backdrop of glowing material. And to do that, astronomers needed a telescope as large as the Earth. No single observatory can resolve an object as small and distant as a black hole's event horizon. But by cleverly combining radio telescopes scattered across the globe, scientists created a virtual Earth-sized telescope with astonishing acuity. This worldwide network was aptly named the Event Horizon Telescope. At a specific wavelength of radio light, each telescope in the array observed the same black hole in concert, their signals meticulously time-stamped by atomic clocks. Later, supercomputers combined these signals, using a technique called interferometry, to synthesize an image with a resolution far beyond what any single dish could achieve. The target of this ambitious project was a supermassive black hole in the galaxy M87, a giant elliptical galaxy roughly 55 million light-years away. Earlier studies had indicated a huge mass in its core, about 6.5 billion suns, and a colossal jet shooting outward at nearly the speed of light. If any black hole's silhouette was going to be observable, M87's was a prime candidate. Enormously massive, which makes its shadow larger, and surrounded by bright emission from infalling gas. After years of planning and a week-long observing campaign in 2017, the team collected petabytes of data stored on high-speed drives. It took 2 more years of careful analysis to produce the picture that made headlines around the world in April 2019. A fuzzy but distinct ring of light, glowing orange in the false color image, with a dark center. That glowing ring is light emitted by superheated gas just outside the event horizon. The gas in that region is orbiting the black hole at fantastic speeds, close to the speed of light. As it swirls, it heats up and radiates, especially in radio waves and submillimeter waves that can travel through intervening dust. The black hole itself casts a shadow on this emission by capturing the photons that stray too near. What we see is effectively a silhouette, a dark central spot where the black hole's gravity has trapped light, encircled by a bright ring where light is bending around the black hole and escaping. This bright outline is sometimes called the photon ring or light ring. It arises because the black hole's gravity can corral light into circular orbits. Photons that come in at just the right angles skim the edge of the black hole, looping around it one or more times before heading toward our telescopes. Most of these orbits are not stable. Eventually, the photons either fall in or escape outward. But the net effect is a bright, thin region of concentrated light outlining the shadow. In reality, there are multiple nested rings of light, each corresponding to photons that loop around the black hole an additional time. The first image we captured wasn't sharp enough to distinguish these subrings. It showed a blended, fuzzy donut of emission. Yet, just detecting this structure was a triumph, confirming predictions of general relativity in exquisite detail. One remarkable aspect of the image was its close agreement with theory. The diameter of the dark shadow in M87's nucleus corresponded to what physicists expected for a black hole of its calculated mass, given the distance. The ring appeared somewhat brighter on one side, which is interpreted as the side where gas is rotating towards us. Due to its high speed, that side's emission is boosted, a relativistic beaming effect, whereas the far side, rotating away, is dimmed. This brightness asymmetry was another anticipated feature, consistent with a rotating accretion flow around a spinning black hole. Encouraged by the success with M87 star, the Event Horizon Telescope team next turned to the center of our own galaxy. There lurks Sagittarius, a star, a supermassive black hole about 4 million times the mass of the Sun. It's much closer to us, just 26,000 light-years away, but also much smaller in mass, so its shadow, seen from Earth, appears roughly the same apparent size as M87's. Imaging Sagittarius. A star proved even harder than imaging M87 star. The gas around our black hole is turbulent, and the emission changes on timescales of mere minutes, because the orbital time near a smaller black hole is shorter. This is like trying to photograph a flickering candle flame, and moreover, our galaxy's center is shrouded in interstellar dust that blurs radio waves slightly. Nonetheless, in 2022, astronomers unveiled a portrait very similar to M87's, a ring of radio glow about 50 microarcseconds across, once again cradling a dark center. It was the long-anticipated glimpse of the Milky Way's own central dark heart. These images do not show the black hole itself. No light comes directly from the event horizon or within, but they are visual proof of the black hole's existence and size. They also provide new measurements. By fitting models to the ring, scientists can estimate the black hole's mass and even constrain its spin. For instance, M87's image, together with information about its jet, suggests that the black hole is indeed rotating and likely powers the jet through magnetic effects. For Sagittarius, a star, the image confirmed the mass to be around 4 million suns, matching the value determined by observing stars orbiting it, a method we will soon explore. Any discrepancies would have hinted at new physics, but so far, the observations align well with Einstein's gravity. To achieve such resolution, every detail mattered, Telescopes at high altitudes were chosen to minimize atmospheric water vapor, which can absorb the sub-millimeter radio waves used. The array included observatories in diverse corners of the world: mountains in Hawaii and Spain, plateaus in Chile, deserts in the American Southwest, and even a station at the South Pole. By spanning as large a distance as possible across Earth, the array attained maximum resolving power. Still, gaps in coverage meant the image had to be reconstructed, using algorithms that filled in missing pieces in a plausible way. The team ran many tests to ensure the final image features were real and not artifacts. The end result, humanity's first photo of a black hole's immediate vicinity, sparked wonder around the globe. Beyond the iconic images, this technique holds promise for the future. As more telescopes are added to the network and technology improves, we may sharpen these images and possibly even produce movies of gas orbiting the black hole in real time. One day, we might resolve the predicted substructures within the photon ring, testing general relativity's predictions to new limits. We might watch as a bright hotspot of infalling material swings around the back of the black hole and reappears, its light delayed and bent by the strong gravity. Such dynamic imaging would open an unprecedented window into the behavior of gravity in its most extreme regime. For now, seeing that glowing ring and dark shadow is a breathtaking confirmation of theory turned into reality. It's one thing to calculate that a black hole should cast a shadow. It's another to look at the sky and see that shadow staring back. These observations bring us as close as we can get to looking at a black hole. The experience is akin to finally seeing the face of a long-suspected, elusive entity. The black hole, once purely a creature of thought experiments, has become palpably real in the form of that orange ring of light. While the images of M87 star and Sagittarius, a star, were celebrated as monumental achievements, they are part of a broader effort to measure and understand black holes through many means. Imaging gives us a direct size and an impression of the environment. But to truly weigh a black hole and map its influence, we also rely on the motions of objects bound to it by gravity. In our galactic center, for example, it was the decades-long observation of orbiting stars that provided irrefutable evidence of a massive black hole years before any image was possible. We now turn to those methods of weighing the giants, tracking stars and gas as they respond to the heavy presence of a black hole. High above the crowded stars of the Milky Way's core, astronomers fixed their telescopes on an apparently unremarkable patch of sky, invisible to ordinary eyes, buried behind clouds of galactic dust. The center of our galaxy was quietly busy. There, stars orbit something unseen with astonishing speed. One star in particular, known as S2, became the focus of intense observation. Over long years, astronomers traced its path and were stunned by what they found. S2 was in a highly elliptical orbit, swinging in close to an unseen object and then hurtling back out, completing a circuit every 16 years. At its closest approach, S2 comes within about 17 light-hours of the galactic center, roughly 4 times the distance from the Sun to Pluto. In cosmic terms, this is extremely close to the nucleus of a galaxy. And at that periapsis, the star is moving at over 2% the speed of light, roughly 25 million kilometers per hour. Only an immense gravity could whip a star around so fast on such a tight leash. By applying Kepler's laws of motion, scientists calculated that the mass pulling on S2 is about 4 million times that of our Sun, confined in a region no larger than our solar system. No cluster of normal stars, no swarm of dead neutron stars, nothing except a supermassive black hole could fit so much mass into such a small space without any visible light. This painstaking work of watching stars orbit the invisible was rewarded with a profound confirmation. Our Milky Way harbours a central black hole, now commonly referred to as Sagittarius A star. Two independent teams, using large telescopes in Chile and Hawaii, patiently charted the positions of S2 and other nearby stars over decades. They witnessed S2's dramatic swing around the dark centre in 2002 and again in 2018. As the star sped through its closest approach, its light was stretched to redder wavelengths by the intense gravity, a subtle effect predicted by Einstein's theory. Even the orbit itself shifted slightly with each loop, tracing a rosette pattern rather than a perfect ellipse, another relativistic signature. These observations left little doubt. At the heart of our galaxy lies a supermassive black hole, silently governing the orbits of stars. Sagittarius. A star's mass, deduced from these stellar orbits, agreed with earlier, rougher estimates from radio observations of gas swirling around the centre. But the stellar data provided a leap in precision and certainty. They not only weighed the black hole, but also established an upper limit on its size. Given the mass and the orbital distance of S2, the object had to be smaller than that orbit. In fact, it must be no bigger than about 17 light-hours across. For perspective, light-hours are a measure of distance light travels in an hour. The orbit of Neptune is about 8 light-hours in diameter. So all 4 million solar masses are packed into a region comparable to or smaller than a giant planet's orbit. This is consistent with a black hole's dimensions, reinforcing the conclusion that nothing else could be hiding there instead. The technique of weighing a black hole by observing orbital motions is a fundamental tool in astronomy. It's essentially the same method used by Isaac Newton to deduce the Sun's mass from Earth's orbit, or by astronomers to find unseen planets around distant stars. By measuring how fast an object orbits and how far it is from the centre, one can infer the central mass. In the case of black holes, the challenge is that the central object is invisible. But the principle holds. Besides the Milky Way, many other galaxies have yielded their secrets to this technique. In giant elliptical galaxies or nearby spirals, astronomers measure the rapid motions of stars or gas near the core. Often, they find that these motions are too fast to be accounted for by the visible stars alone. An enormous dark mass must be present. In galaxy after galaxy, the numbers come out to millions or billions of solar masses confined to a tiny volume, pointing to the ubiquity of supermassive black holes. A beautiful example comes from a galaxy called NGC 4258, where nature provides a special tool. Here, a disk of gas and dust orbits the central black hole, and within that disk are molecules of water acting as cosmic lasers, masers. These water masers emit radio waves of a very precise frequency and can be observed with superb accuracy. By using radio telescopes, astronomers mapped the positions and velocities of these maser spots in the disk. Remarkably, they traced nearly perfect circular orbits. The measurements showed that the orbital velocity of the maser clouds changed with distance in exactly the way Kepler's laws predict for a central point mass. From the innermost orbit to the outermost one observed, the velocities fit a neat curve corresponding to a central mass of about 40 million suns. The data was so precise that it not only nailed the black hole's mass, but even allowed scientists to calculate the distance to that galaxy purely geometrically. The presence of a supermassive black hole in NGC 4258 was thereby confirmed with textbook clarity. Maser studies and stellar orbits are direct and vivid ways to determine black hole masses. In other galaxies, where we cannot see individual stars or discrete maser spots, astronomers rely on the aggregate motions of whole swarms of stars or gas. By taking spectra of the galaxy's core, they measure how the star's light is broadened by their random motions, or how gas emission lines are broadened by rotation and turbulence. The degree of broadening indicates the velocities present, and those in turn reflect the pull of gravity. Through sophisticated models, a central mass can be inferred. Using the Hubble Space Telescope and large ground-based telescopes, dozens of galactic nuclei were surveyed. The results revealed a strong pattern. Virtually every sizable galaxy has a central dark mass proportional to the galaxy's bulge. This relation, often called the M-sigma relation for mass and velocity dispersion, suggests that the growth of black holes and their host galaxies are closely intertwined. Even on the scale of stellar mass black holes, orbital dance reveals mass. In X-ray binaries mentioned earlier, the visible star's orbit around an unseen companion yields the companion's mass. If it exceeds about 3 solar masses, the maximum mass a neutron star can have before collapsing, then the companion is almost certainly a black hole. By applying this logic, astronomers have confirmed on the order of dozens of stellar black holes in our Milky Way and nearby galaxies long before they could ever be seen directly. Each of these dynamical methods, whether it's tracking a star, a gas cloud, or analyzing the collective motion of many stars, gives us a way to weigh black holes. These measurements not only prove that the dark objects are indeed extraordinarily massive, but they also provide essential data for understanding black hole demographics. We learn how massive black holes typically are in galaxies of different sizes. We can study how some black holes seem to have grown more than others, or how interactions and mergers of galaxies might lead to the mergers of their central black holes as well. The saga of Sagittarius. A star is also a story of technological progress. The object had been known since the 1970s as a compact, bright radio source in the galactic center, strongly suspected to be a black hole. However, early instruments lacked the resolving power to see stars moving around it. It wasn't until the 1990s and 2000s, with advancements in adaptive optics and infrared imaging, that astronomers could pick out individual stars dancing around the invisible mass. The clarity of the evidence gathered by those teams was so compelling that it earned them one of the highest honors in science, a share of the Nobel Prize, for finally proving beyond doubt that a supermassive black hole anchors our galaxy. Even now, the quest continues. New telescopes and improved techniques seek to find even closer stars or gas clumps in tighter orbits around Sagittarius A star. Each new discovery pushes the boundary of how near we can observe matter circling the point of no return. If a star orbits close enough, its motion might reveal not just the mass of the black hole, but also how that mass might be spinning by subtle shifts in its orbit caused by frame dragging of spacetime. We have not yet found such a fortuitously close star, but ongoing surveys keep watch for any hints of matter moving in those extreme depths of the gravitational well. These efforts promise to deepen our understanding even further, turning the black hole from an inferred presence into a well-characterized celestial object governed by known physics. Having established the mass and presence of black holes through their gravitational influence, we can delve into deciphering the detailed conditions in their immediate vicinity. That calls for listening to the fine tonalities in the spectrum of light emitted by the matter in their grip. Like forensic clues, the fingerprints in that light can tell us about velocities, temperatures, and even the warping of space-time itself near the event horizon. In the next step of our journey, we examine how the light's spectrum and timing reveals the secrets of accretion disks and the space-time around black holes. The light that reaches us from a black hole's surroundings is more than just a beacon. It is also a bearer of secrets. Imprinted in that light are subtle fingerprints left by the extreme gravity and rapid motions near the event horizon. By carefully dissecting the light into its component colors, or energies, astronomers have found telltale spectral lines and timing signals that reveal conditions in places we cannot directly see. These spectral clues allow us to probe the space-time near black holes in much the same way a detective might examine clues at a crime scene to infer what happened. One of the most striking examples comes from iron, a common element in cosmic gas. In the inner regions of an accretion disk, iron atoms can be excited to emit X-ray light at a very specific energy. Under normal conditions, iron produces a sharp spectral line, like a well-defined note on a musical scale. But near a black hole, this iron line is anything but sharp. When astronomers observed certain black hole systems with X-ray telescopes, they discovered that the iron line had been broadened and skewed into a distinctive shape. Instead of a narrow peak at its usual energy, the line was spread into a broad plateau with a faded tail extending to lower energies. This was a powerful clue. Such a profile is exactly what one would expect from iron glowing in the grip of extreme gravity and speed. The reason for this broadening lies in the relativistic forces at play. Close to the black hole, matter in the disk orbits at a significant fraction of the speed of light. As iron-rich gas whips around, the light it emits from the side moving toward Earth is compressed, blue-shifted, to slightly higher energies, while light from the receding side is stretched, red-shifted, to lower energies. This Doppler effect alone would make the line broader. On top of that, the immense gravity near the black hole drains energy from the photons climbing out of the potential well, a gravitational redshift that shifts the entire line toward lower energies and further blurs its shape. The combination produces a telltale asymmetric line, a steep cutoff on the high energy side from the approaching gas, and an extended tail on the low energy side from gravitational redshift of light that struggles to escape. Detecting this relativistically smeared iron line was like hearing a familiar tune played on a distorted instrument, revealing the influence of the black hole on the emission. It provided direct evidence that material was indeed orbiting deep in the gravitational field, likely very close to the innermost stable orbit around the black hole. By fitting the detailed shape of this line, scientists can infer how close the inner edge of the disk comes to the black hole. If the disk extends very close to the event horizon, it suggests the black hole is rapidly spinning, since a spinning black hole's inner stable orbit can be closer in than that of a non-rotating black hole. Conversely, if the line indicates the disk stops farther out, the black hole might have a more modest spin. In this way, the iron line serves as a cosmic speedometer and tape measure, gauging both orbital velocities and distances in the very vicinity of the black hole. Beyond static spectral lines, black holes also reveal themselves through the timing of their light variations. The environment around a black hole is dynamic. Clumps of gas move, flare up, or disappear as they spiral inward. These changes produce flickers and flashes in the emitted light. In the realm of massive black holes at galactic centers, astronomers use a technique called reverberation mapping to make sense of these flickers. The idea is akin to listening for an echo in a canyon to judge the distance of the canyon walls. At the center of an active galaxy, there is often a bright source of ultraviolet or X-ray light, presumably from the innermost accretion flow, or a hot corona of electrons above the disk. Surrounding this bright source, a bit farther out, are clouds of gas that absorb and re-emit some of that light, each cloud producing emission lines, for example, from hydrogen or other elements. When the central source changes in brightness, let's say it suddenly brightens, The nearby gas clouds respond by emitting more light, but not instantly. There's a slight delay because the light must travel out to the clouds and then back to our telescopes. By measuring that time delay between the central continuum flare and the response of the emission lines, astronomers can gauge the distance to those clouds. Reverberation mapping has been especially useful for estimating the size of the broadline region in quasars and active galactic nuclei. These broadline regions are made of gas moving at thousands of kilometers per second under the influence of the black hole's gravity, producing broad spectral lines in the optical and ultraviolet. With the time delay from reverberation mapping, say a delay of a few days or weeks between continuum changes and line responses, scientists can deduce that the gas clouds lie a few light days or light weeks from the center. Knowing this distance and measuring the speed of the gas from the width of the lines, one can apply the laws of gravity to estimate the mass of the central object. Essentially, the gas clouds are orbiting the black hole, and by timing their echoes, we can chart the size of that orbit. This method has allowed black hole mass estimates for extremely distant quasars, extending the reach of weighing black holes to the far corners of the universe where individual stars or masses cannot be observed. Reverberation is not limited to optical light. In recent years, astronomers have also used X-ray reverberation to probe the innermost accretion disk itself. In an active galaxy's core, or even around stellar black holes, there is often a region of very hot electrons, called the corona, close to the black hole, which emits energetic X-rays. Some of these X-rays shine onto the disk and get reflected, producing features like the iron line we discussed. If the corona's brightness fluctuates, the reflected light from the disk will flicker in response, but slightly later. By measuring such X-ray echoes, for instance, noticing that a sudden spike in X-rays is followed, a few milliseconds or seconds afterward, by a corresponding spike in the iron line emission, researchers can measure the light travel time between the corona and the disk. These delays often indicate that the X-ray emitting region is extremely compact and very close to the black hole, perhaps just a few times the radius of the event horizon above the disk. This in turn tells us something about how the X-ray source, the corona, is arranged in the system, perhaps hovering above the black hole's pole or sandwiched between disk layers. Essentially, X-ray reverberation mapping offers a way to construct a mental map of the innermost regions of the accretion flow, timing out the distances between the black hole, the inner disk, and the high-energy light source. Apart from echoes and lines, black hole systems also exhibit quasi-periodic oscillations, or QPOS, which are rhythmic flickers in their light. In some accreting stellar mass black holes, for example, astronomers have noticed that the X-ray brightness rises and falls in a pattern that repeats nearly regularly, with frequencies of several hundred times per second in certain cases. These high-frequency QPOS are thought to reflect oscillations in the inner disk, or orbiting hotspots of gas whipping around the black hole. One intriguing possibility is that these oscillations correspond to matter circling at the innermost stable orbit, bumping and bobbing in the curved spacetime. If true, the frequency of the QPO can directly relate to the black hole's mass. Heavier black holes would have slower orbital frequencies at a given radius, and potentially its spin, since spin changes the orbital period at the innermost edge. In heavier supermassive black holes, similar oscillations would be too slow to notice easily, but in stellar black holes they enter the audible range if converted to sound, like a drum beat coming from the vicinity of the event horizon. Another diagnostic comes from the overall shape of the emitted spectrum from an accretion disk. A disk of gas around a black hole has a range of temperatures, cooler at the outer edges and hotter towards the inside. This means it doesn't emit a single color of light, but rather a broad continuum with a peak at a certain wavelength corresponding to the hottest part of the disk. By modeling this spectrum, scientists can infer how far in the disk extends. If the black hole is spinning quickly, the disk can extend deeper, closer to the event horizon, before the plunge, reaching higher temperatures and emitting slightly different radiation than if the disk is cut off further out around a non-spinning black hole. In practice, for stellar black holes in binary systems, fitting their X-ray spectra when they are in a soft disk-dominated state has enabled estimates of the inner disk radius, and thus the black hole spin. It's a subtle measurement, requiring precise calibration and understanding of the system, but it's one of the few ways we have to measure a black hole's spin, complementing the iron line method. All these spectral and timing tools, iron line profiles, emission line echoes, X-ray reverberation, QPOs, and continuum fits, form a kind of toolkit for astronomers peering into the vicinity of black holes. Each tool provides a piece of the puzzle. The iron line tells us about velocities and gravitational redshift in the inner disk, hinting at how fast space is rotating and how deep the gravitational well is. Reverberation mapping lays out distances and sizes, effectively giving a map of where things are around the black hole. QPOS give us hints of orbital motion, and perhaps the whisper of strong field gravity acting on clumps of matter. And the broad spectral energy distribution of disks helps confirm how energy is released as material spirals inward. These clues have led to some remarkable insights. For instance, we now know that many supermassive black holes are spinning, some at rates approaching the theoretical maximum, where the event horizon itself would be dragged into a more flattened shape. We've learned that the accretion disks in active galaxies often extend down to the innermost stable orbit, supporting the idea that those black holes are fed efficiently. We have evidence that the light we see from these disks sometimes comes from regions just a few times the distance of the event horizon itself, an affirmation that our observations are genuinely probing the edge of the abyss. Through the prism of a black hole's light, we are sensing effects like gravitational redshift and frame dragging, phenomena otherwise encountered only in equations or thought experiments. While much has been gleaned from these spectral diagnostics, interpreting them is complex. It requires matching observations with detailed theoretical models of how light is emitted and altered near a black hole. This is where another hero of modern astrophysics comes into play: large-scale numerical simulations. To truly understand and predict what these spectral clues are telling us, researchers simulate the behavior of matter and light in the vicinity of black holes using powerful supercomputers. These simulations, our next topic, allow us to test whether our interpretations of spectral signals hold up under the known laws of physics operating in extreme conditions. When the laws of physics venture into realms beyond everyday experience, our intuition can falter. Black holes, with their intense gravity and swirling plasma, present environments where equations rule more reliably than mental pictures. To bridge the gap between theory and observation, scientists turn to the power of computation. In supercomputers, they recreate miniature universes governed by Einstein's general relativity and the complex physics of plasmas. Here, they can conduct experiments that would be impossible in reality, watching eons of cosmic evolution unfold in hours, pausing or rewinding the drama around a black hole at will, and extracting details of every particle's journey. This is the realm of numerical simulations, where day-to-day concepts of time and space give way to algorithms and code. A realm poetically described as a numerical nightfall, where we simulate the darkness itself. A typical black hole simulation begins with a simple setup: a spinning black hole inserted into a virtual grid representing space, surrounded by a cloud or disk of gas and threaded by magnetic field lines. Then, the equations of motion take over. Under the relentless pull of gravity, the gas begins to swirl inward. Friction and shock waves within the gas heat it to incandescence. Magnetic fields, dragged along by the rotating plasma, twist into complex shapes. In the simulation's mathematical eye, we can see turbulence developing, eddies of hot gas, spiraling filaments, and sometimes the formation of a pair of tight, collimated jets spearing out along the black hole's rotational axis. These simulations are a marvel of modern computational astrophysics. They must solve highly nonlinear equations of magnetohydrodynamics, the behavior of electrically charged fluids in the curved spacetime around a black hole. The resolution needs to be fine enough to capture a tiny region near the event horizon, and large enough to include regions far out where the jets might extend. Each increment of time, maybe a tiny fraction of a second of simulated time, requires calculating how gravity, pressure, magnetic forces, and relativity affect every zone of the grid. The world's fastest computers often spend days or weeks crunching the numbers for a single detailed simulation. What emerges is a blow-by-blow account of what matter and fields do in one of the most extreme places in the universe. The reward for all this effort is profound insight. Simulations have shown, for example, how magnetic fields can act like an engine powering jets. In some runs, as the disk plasma spins, magnetic field lines get wound up tightly by the rotating black hole, tapping into its rotational energy. If conditions are right, they can fling matter outward in narrow beams at nearly light speed, a digital replay of how real quasars likely shoot out their radio jets. Through such experiments in silico, we've come to believe that rapidly spinning black holes with strong magnetic fields are the launch sites of the universe's most powerful particle accelerators, the jets that we observe spanning intergalactic space. These numerical models also allow scientists to produce synthetic observations, which they can compare with actual data. For instance, after running a simulation of gas flowing into a black hole, researchers can take the output, the distribution of density, temperature, and velocity of the gas, and then compute what an observer would see. They use ray tracing codes that send test light rays through the simulated environment, bending around the black hole according to general relativity. The result might be an image or spectrum that can be directly compared with what a telescope like the Event Horizon Telescope or an X-ray observatory records. It's in these comparisons that theory meets reality. Remarkably, many features of the first black hole images were anticipated by simulations. The donut-like ring of light, its diameter, and even hints of brightness asymmetry due to the plasma's motion. The simulations help confirm that what we think we are seeing is indeed consistent with a spinning black hole wrapped in a glowing disk. Simulations don't just reproduce expected phenomena. They often reveal surprises lurking in the equations. As an example, when first modeling black hole accretion disks, researchers discovered a natural instability that breaks the smooth disk into a clumpy, variable structure. This instability, driven by the magnetized plasma's dynamics, causes the disk to have turbulent internal life. Sometimes dense knots of gas form and fall into the black hole in spurts. Such behavior can explain why real accretion disks flicker and flare instead of shining uniformly. Likewise, simulations of two black holes spiraling together not only produce gravitational waveforms that match what LIGO detected, the rising chirp, and sudden cutoff of a merger, but they also showed that right after the merger, the new merged black hole can kick away at high speed. This happens due to asymmetrical emission of gravitational waves, a nuance that analysts gleaned from the simulations and later identified as a possibility in actual gravitational wave data. The ability to simulate tidal disruption events has added layers to our understanding of those stellar deaths as well. Virtual stars can be sent on trajectories that skim too close to a simulated black hole. One can watch as the star stretches into a spaghetti-thin stream under tidal forces. The stream wraps around the black hole, colliding with itself and forming a temporary accretion disk. These models predict how the flare should rise and decay in brightness, helping observers know what to look for and how to interpret the light curves and spectra from real events. In some cases, simulations have predicted that a star might not be completely destroyed on the first pass, but could shed mass in multiple swoops around the black hole, leading to a flare with multiple peaks. And indeed, a few candidate events with such patterns have been observed. Perhaps one of the most visually striking uses of simulation has been to create realistic visuals of black holes. By calculating how light would travel around a black hole, including all the lensing and warping effects, scientists can generate what a hypothetical camera might see if it were hovering near the event horizon. These visualizations show the full glory of gravitational lensing. The accretion disk appears to wrap above and below the black hole due to light bending, and a thin photon ring is visible as a perfect circle, the last orbit of light itself. Such images were popularized when a blockbuster film consulted physicists to depict a black hole realistically. The glowing, bent accretion disk and halo of light around a shadow were directly informed by physics calculations. In science, the same approach is more than just for show. It helps researchers anticipate what new telescopes should observe. For instance, as the Event Horizon Telescope continues to improve, scientists use simulations to guess how a black hole movie might look, perhaps spotting hotspots orbiting or jets wobbling if the black hole's spin is tilted relative to the disk. Simulations serve as a virtual laboratory to test ideas that we cannot experiment on in reality. Want to know how a black hole's environment changes if it spins at 99% of the maximum rate versus 50%? Run 2 simulations and compare the strength of jets or the efficiency of accretion. Curious what happens if 2 unequal mass black holes collide? Set them up in a simulation and see how gravitational waves radiate and how the final black hole might recoil. These computational experiments guide our interpretations of observations. If a real observation shows something unexpected, researchers can tweak a simulation to try to reproduce it, thereby hypothesizing what physics might be at play. Of course, simulations are only as good as the physics we put into them. As our understanding deepens, more ingredients get added. More realistic handling of how radiation flows and cools the gas. Better resolution. Inclusion of effects like relativity in the radiation, not just in gravity. Early simulations might have oversimplified some processes, but over time, they have grown increasingly sophisticated. We can now simulate an accretion disk and also track the radiation pressure it exerts, or model how the disk's winds carry matter away under the black hole's intense radiation. In the grand symphony of black hole astrophysics, numerical simulations play a key supportive role. They help orchestrate our theories with the melody of observations. They ensure that the beat of gravitational waves or the chorus of X-ray signals align with what known physics would produce. When discrepancies arise, it signals that either the simulation missed something or perhaps our physical understanding is incomplete, leading to refinements in both theory and code. Through simulations, black holes have become not just enigmatic cosmic objects, but also tangible environments we can explore virtually. We have, in a sense, created digital twin black holes on our computers, allowing us to fall into them vicariously, to test rescue strategies for photons trying to escape, or to watch magnetic fields gyrate in a dance macabre around the void. This synergy of observation, theory, and simulation has greatly advanced our comprehension. And yet, there is so much more to learn. The more we simulate and observe, the more questions arise. To answer them, we look to the next generation of tools. New telescopes and detectors that will expand our senses, capturing signals from black holes that have so far eluded us. In our journey's next chapter, we turn our eyes and ears to these future instruments, poised to deepen the exploration of the unseen. Even as we celebrate the breakthroughs of recent years, astronomers are preparing for the next revolution in observing the invisible. New instruments, both on the ground and in space, promise to sharpen our vision and extend our hearing, giving us unprecedented access to black holes and their antics. Each upcoming project can be thought of as a new sense, a way to perceive the universe that was previously out of reach. Together, these next eyes and ears will work in harmony, capturing cosmic events from multiple angles and through different messengers. One of the most eagerly anticipated advancements is a space-based gravitational wave observatory named LISA, Laser Interferometer Space Antenna, where current gravitational wave detectors, like LIGO, listen to high-pitched chirps from stellar mass black holes merging. LISA will tune in to the low bass notes of the cosmos. It will consist of 3 spacecraft flying in a triangular formation millions of kilometers apart, using laser beams between them to sense the stretching and squeezing of spacetime. This enormous scale allows LISA to detect waves far longer than LIGO can, waves that take minutes or hours to oscillate instead of fractions of a second. Those gentle ripples will come from colossal sources, merging black holes that are millions of times the mass of the Sun, slowly spiraling together in distant galactic mergers. If 2 galaxies collide and their supermassive black holes dance toward union, LISA will be able to hear their approaching footsteps, perhaps years before the final merger. It will also pick up other exotic events, like a smaller black hole slowly spiraling into a giant one, a sort of extreme orbital dance that can map the space-time geometry of the big black hole. Or maybe signals from the early universe that carry information about the newborn cosmos. With LISA's launch planned in the 2030s, our ears will extend to the farthest reaches of time and space, capturing the gravitational chorus of the universe in a new register. Imagine being able to detect the merger of 2 supermassive black holes in a galaxy billions of light years away, an event that might not produce any light we can see, but which will cause space itself to ring like a giant bell. Such an observation would let us test gravity in regimes even more extreme than those accessible now, and it would connect directly with electromagnetic astronomy. For example, if a pair of supermassive black holes is detected by LISA as they spiral, telescopes on Earth and in orbit could be alerted to look for any flicker of light from the galaxy in question. Perhaps they will see a burst of light as the final merger shakes the surrounding gas or causes a jet to realign, or maybe nothing at all. Either outcome tells us something about the environment of such a merger. That kind of coordinated observation, using gravitational waves as a trigger and electromagnetic waves for follow-up, or vice versa, is the essence of the emerging multi-messenger approach to astronomy. Meanwhile, on Earth, plans are underway for even more advanced gravitational wave observatories. Future facilities like the Einstein Telescope and Cosmic Explorer are envisioned to vastly improve our sensitivity to cosmic ripples, potentially catching mergers of black holes from the early universe and intermediate mass black holes that have so far evaded detection. Together with LISA, these next-generation instruments will cover a broad spectrum of gravitational waves, ensuring that no cosmic collision goes unheard and extending our reach deeper into cosmic history. On the seeing side of things, plans are underway to greatly enhance the Event Horizon Telescope that gave us our first glimpse of a black hole's shadow. The next generation EHT, NGEHT, will involve more radio telescopes, some newly built and others repurposed, spread over the globe to increase the array's fidelity and coverage. The goal is not only to take still images of black holes, but to capture video, to watch how the pattern of the glowing gas around a black hole changes over time. With a sharper and faster view, we might witness orbiting hotspots in the accretion flow, perhaps even tracing out one full loop around the black hole, or see the base of a jet wobbling if the black hole's spin axis is precessing. The NGEHT will also try to resolve finer details of the photon ring. As discussed, the photon ring is actually a series of subrings, each lapping the black hole one additional time. With improved sensitivity and resolution, there is hope to detect at least the strong signature of those subsequent rings, or at least better constrain their presence, further validating the predictions of general relativity. Engineers and scientists are also looking at extending these Earth-sized arrays beyond Earth. Concepts have been floated for putting a radio telescope in orbit or on the Moon to join the network, which would increase the effective size of the telescope and thus the detail in the images. Even without leaving Earth, simply adding more stations in currently sparse regions, like Africa or the oceans, will fill in gaps in the EHT's coverage, yielding clearer pictures. It's a bit like having more pixels in a camera sensor. By the time these improvements are in place, perhaps we will have crisp images of many black holes, not just M87 and Sagittarius A star. We could map the magnetic fields at the edge of a black hole by imaging polarized light with high resolution, revealing how those fields thread through the plasma and possibly drive the jets. We might even catch transient events. Imagine an image of a black hole devouring a chunk of star, and suddenly the ring of light becoming asymmetrically brighter as a surge of new matter flows in. Another frontier is the systematic capture of brief and unpredictable cosmic events, the realm of time-domain astronomy. Upcoming observatories like the Vera C. Rubin Observatory, formerly known as LSST, the Large Synoptic Survey Telescope, are designed to survey the entire visible sky night after night, alerting us to anything that changes. This means no dramatic outburst should go unnoticed. If a star is torn apart by a black hole in some distant galaxy, for example, Rubin's wide-field eye could catch the sudden flare of light and flag it for astronomers to study in detail. We expect to discover many more tidal disruption events this way, building a better statistical understanding of how often they occur and what the range of behaviors can be. Some might have jets, some might be obscured by dust. Frequent discoveries will fill in the diversity. Time domain surveys will also monitor active galaxies for sudden changes, perhaps catching a normally quiet nucleus abruptly turning into a quasar-like beacon, or conversely, a bright quasar dimming as its fuel runs low. These surveys don't work alone. They operate in tandem with rapid response telescopes across the electromagnetic spectrum. When a new transient is found, X-ray and radio telescopes can quickly follow up to see if X-rays or radio waves are also flaring, building a complete picture. In one scenario, a gravitational wave detector might pick up the signal of a neutron star being captured by a black hole, and within seconds, automated systems will point optical and X-ray telescopes to that region, hoping to witness any flash or afterglow from the event. In another scenario, a neutrino observatory like IceCube might detect a high-energy neutrino, a ghostly particle that rarely interacts, coming from a certain patch of sky. This could indicate that a black hole's jet has accelerated some particles to extreme energies, producing neutrinos. Telescopes can then examine that patch for an active galaxy or blazar in a high state of activity. This happened in 2017. A neutrino detection led astronomers to pinpoint a flaring blazar, providing the first solid evidence that black hole jets are one source of cosmic neutrinos and high-energy cosmic rays. This multi-messenger synergy, combining light, gravitational waves, neutrinos, and who knows what other signals, represents the future of astrophysics. Black holes, which were once studied solely through the light of X-rays or radio waves, can now be approached through their gravitational imprint and even through elementary particles they fling our way. Each messenger carries different information. Gravitational waves carry a detailed record of the motions and masses. Neutrinos tell of the most high-energy particle interactions, and electromagnetic waves show us the heat, magnetic fields, and radiation processes at work. By piecing these together, we get a much richer narrative of what's happening near a black hole. As we stand on the cusp of this new era, we can anticipate many surprises. Perhaps Lisa will detect something utterly unexpected, a kind of gravitational wave signal that theorists have not predicted, hinting at new physics or unseen populations of black holes. Maybe the next generation event horizon imaging will spot phenomena around black holes that challenge our current models, like mysterious patterns in the photon ring or an odd wobble that could indicate the presence of a second black hole nearby. Time domain surveys might catch the moment a black hole switches on after eons of slumber, giving us a literal before and after portrait of a galaxy's nucleus coming alive. The beauty of science is that each new tool not only answers old questions, but also raises new ones. With every improvement in our eyes and ears, the cosmos reveals a bit more of its complexity. Black holes, the once purely theoretical oddities, are now central actors on the stage of modern astronomy. Our ability to observe them has grown from indirect inferences to direct imaging and listening to their space-time vibrations. And yet, many mysteries remain. What really happens at the edge of a black hole, where quantum effects might come into play? Do black holes somehow influence the evolution of life by seeding galaxies with heavy elements through their explosions and outflows? Could we ever find a way to retrieve information that falls into a black hole, solving the so-called information paradox? These questions linger as we refine our instruments. What lies ahead is not just the gathering of more data, but a deeper synthesis of knowledge. By uniting insights from all these approaches, from gravitational waves to gamma rays, from neutrinos to radio maps, we inch closer to a holistic understanding of black holes. Each messenger and each observation technique is like a different language, and we are slowly becoming fluent in all of them, translating the full story of black holes. As our journey continues, armed with new technology and a spirit of discovery, we find ourselves on the threshold of answers that have long eluded us. The darkness is a little less impenetrable than before, and the center of the black hole, once a byword for oblivion, is becoming a wellspring of knowledge about the universe. Our voyage is far from over. With new eyes and ears opening, we venture onward, ready to embrace the next revelations on our path to understanding these enigmatic cosmic giants.